Hello there, and welcome to the Sleep Science Calm Stories. I'm so glad you found your way here tonight. Wherever you are in the world, and whatever kind of day you've had, this is a quiet place where you can slow down for a while. A place where curiosity can move gently, and where nothing asks very much of you. You might be settling into bed, or resting on a sofa, or perhaps simply listening in a dim room with the lights low. However you've arrived here, you're welcome to let the day gradually loosen its grip. And if your attention drifts at any point, that's perfectly fine. You don't need to follow every sentence. You don't need to remember every detail. The ideas can simply pass by like distant waves. If you miss something, nothing important is lost. Tonight, we're going to spend some quiet time with a familiar idea: the ocean. Not only the oceans of Earth, but the possibility that oceans may exist on distant planets, far beyond our solar system. Silent seas circling distant stars, water stretching across entire worlds. But before we wander that far out into space, it helps to begin somewhere familiar. Many people have stood beside an ocean at some point in their lives, perhaps on a calm evening, with the sky fading toward darkness and the horizon stretching endlessly in front of them. There is something about the ocean that naturally slows the mind. The steady rhythm of waves, the long horizon, the sense of depth beneath the surface, even when the sea appears calm. We know that vast volumes of water lie quietly below, moving slowly through layers we cannot see. Standing at the shoreline, it's easy to feel that the ocean is enormous, and in a way, it truly is. But as we begin tonight's quiet journey, we'll discover that oceans may not be unique to our world at all. There may be other planets, circling distant stars, where entire global oceans stretch beneath unfamiliar skies, worlds where water covers everything, where no continents interrupt the sea, where distant starlight reflects across silent planetary oceans that no human eye has ever seen. And we'll explore how scientists have begun to imagine these places using only faint signals of light traveling across unimaginable distances. But there's no need to hurry there. For now, we can simply begin with the oceans we already know. And if you enjoy calm explorations of science and the universe like this, you might consider subscribing so you can return whenever you need a quiet place to think or drift toward sleep. Earth's oceans cover more than 70% of the planet's surface. From space, our world appears as a deep blue sphere, wrapped in swirling clouds and vast stretches of water. Continents appear almost like scattered islands within a much larger sea. And when we look at a map of the planet, the oceans dominate the view. The Pacific Ocean alone stretches across such a wide distance that it could swallow entire continents. Yet the surface of the ocean is only the beginning of its story. On average, Earth's oceans are nearly 4 kilometers deep. That's deeper than most mountains are tall. And in certain places, the seafloor drops far deeper still. One of the deepest points on Earth lies in the Mariana Trench in the western Pacific Ocean. At its deepest location, known as Challenger Deep, the seafloor lies almost 11 kilometers beneath the surface. If Mount Everest were placed there, its summit would still be more than a kilometer underwater. Down there, sunlight disappears completely. The pressure becomes immense, and the water grows cold and quiet. Yet even today, with all our modern technology, the ocean floor remains one of the least explored places on our own planet. Large areas of the deep ocean have only been mapped in rough outlines. Some regions have never been directly observed by human eyes. It's a strange realization when you think about it. We have sent spacecraft far beyond the edges of our solar system. We have photographed distant galaxies, but much of the deep ocean here on Earth remains mysterious. Part of the reason is simply the difficulty of reaching such depths. Water is heavy. Every 10 meters of depth adds another layer of pressure pressing inward from every direction. At a depth of 1,000 meters, the pressure is already about 100 times greater than the air pressure we feel at sea level. At the deepest trenches, the pressure becomes almost unimaginable. It's enough to crush ordinary machines instantly. And yet, even under those crushing conditions, the ocean is not empty. Far below the surface, strange creatures move slowly through the darkness. Some produce faint glows of light. Others drift almost invisibly through the water. And along the sea floor, entire ecosystems survive in a world without sunlight. It's easy to forget that most of the ocean exists in darkness. The sun's light penetrates only the upper layers of water. Below a certain depth, the ocean becomes permanently night. A vast hidden world lies beneath the thin sunlit layer, where waves move and ships travel. But even that immense ocean, deep and mysterious as it is, represents only a tiny fraction of the water that may exist in the universe. Because the substance that forms our oceans, the simple molecule known as water, is far more common than we once imagined. Water is made of just 3 atoms, 2 hydrogen atoms and 1 oxygen atom. Hydrogen is the most abundant element in the universe. It was created in enormous quantities during the earliest moments after the Big Bang. Oxygen formed later inside stars as nuclear reactions slowly fused lighter elements into heavier ones. And when hydrogen and oxygen meet under the right conditions, they can combine to form water. This means that water can form in many places across the cosmos. Astronomers have detected water molecules drifting through enormous clouds of gas and dust between the stars. These clouds, known as molecular clouds, are the birthplaces of new stars and planetary systems. Inside them, tiny grains of dust act as surfaces where chemical reactions can occur. Hydrogen atoms settle onto these grains, oxygen atoms join them, and slowly, over long stretches of time, water molecules form and freeze onto the dust as ice. In other words, even before planets exist, water may already be quietly forming in the dark spaces between stars. It floats there invisibly, mixed among the gases and particles that will one day collapse into new solar systems. And when a young star begins to form, those icy grains of dust become part of the swirling disk of material that surrounds it. Inside that disk, small particles begin to collide and stick together. Pebbles form, then larger rocky fragments. Over millions of years, these fragments grow into asteroids, comets, and eventually, planets. And many of those early building blocks carry water ice within them, which means that the story of oceans may begin long before a planet itself is fully formed. Tiny fragments of ice drifting through space may already contain the seeds of future seas. And over time, through countless collisions and slow accumulation, Those fragments can gather into worlds where water becomes something much larger, sometimes forming rivers and lakes, sometimes forming hidden oceans beneath ice, and sometimes, perhaps, forming entire planets where water stretches across the whole surface. Worlds where oceans are not just a feature of the landscape, but the landscape itself, and that quiet possibility that distant planets might hold oceans far larger than our own is where our journey will slowly drift next. Because once scientists began discovering planets beyond our solar system, they also began asking a gentle question. If water exists in so many places across space, how many other oceans might already be out there? And that question, how many oceans might exist beyond our own world, becomes easier to ask once we notice something simple. Water, it turns out, is very good at traveling, not quickly and not dramatically, but patiently across the early history of our solar system. Much of the water that would eventually fill Earth's oceans did not begin here at all. Instead, it likely arrived in pieces, frozen fragments, drifting through space long before our planet finished forming. In the young solar system, more than 4 billion years ago, the region around the newborn sun was crowded with countless small bodies. Some were rocky, others were rich in ice. Farther from the sun, where temperatures were lower, water could remain frozen. In those colder regions, small icy objects formed in large numbers, carrying water ice mixed with dust and minerals. Some of these objects were comets, others were water-rich asteroids. They drifted through the outer solar system in quiet orbits, like scattered seeds, and over time, gravitational interactions between growing planets slowly disturbed those orbits. Some icy bodies were pulled inward toward the warmer regions closer to the sun. Occasionally, one would collide with a young planet. The impact might shatter rock and release energy, but it also delivered something else. Frozen water, locked inside the object since the earliest days of the solar system. Over millions of years, many such collisions may have occurred, each one bringing a small addition of water, each one contributing a little more to the growing reservoirs that would eventually become oceans. The process was slow and chaotic, but gradually, as Earth cooled and its surface stabilized, water accumulated. Some may have arrived frozen inside incoming objects. Some may have been trapped in minerals deep inside Earth and later released through volcanic activity. In either case, the result was the same. Water gathered, rain fell, and over long stretches of time, oceans formed. It's easy to imagine oceans as permanent features of Earth, but in reality, they are part of a much longer planetary story, one that began with drifting ice in the darkness of space, and those icy travelers still move quietly through our solar system today. Comets, for example, remain among the most recognizable of these ancient objects. A comet often begins its long journey far from the sun, in distant regions where cold preserves its frozen materials. Its nucleus, the solid center of the comet, is usually a mixture of ice, dust, and rocky fragments. Some are only a few kilometers across, others are larger, but most remain invisible as they move through the outer solar system. Too distant and too dark to see easily. It is only when a comet travels closer to the sun that something begins to change. As sunlight warms the comet's surface, the ice within it begins to transform. Instead of melting directly into liquid water, the ice often sublimates, turning straight into vapor. That vapor escapes from the comet's surface, carrying dust particles with it. Gradually, a faint glowing cloud forms around the nucleus. This cloud is called the coma, and as solar radiation pushes the gas and dust away from the comet, a long, luminous tail begins to stretch outward. From Earth, these tails can appear bright and dramatic, but the material inside them is extremely thin. A comet's glowing tail is mostly water vapor and tiny dust particles spreading out into space. In a sense, every visible comet is releasing part of its ancient water into the solar system, a quiet reminder that frozen reservoirs of water still exist far beyond our planet. But comets are not the only places where water survives in distant cold regions. Many icy bodies, including moons orbiting the giant planets, also contain enormous amounts of frozen water. And in some surprising cases, those frozen surfaces hide something remarkable beneath them: entire oceans. Take the moon Europa, for example. Europa orbits Jupiter, wrapped in a bright crust of ice that reflects sunlight like polished glass. At first glance, the surface appears cold and still, but scientists studying Europa noticed something unusual about its surface patterns. The ice is crisscrossed with long dark lines and fractures. Some regions appear as though the ice has cracked, shifted, and refrozen many times. These patterns suggested that the surface might not be entirely rigid. Instead, it might be floating above something softer. And eventually, researchers proposed a striking possibility. Beneath Europa's icy shell, there may be a global ocean, an ocean of liquid water, hidden beneath kilometers of ice. The idea seemed surprising at first. Europa is far from the sun, much farther than Earth, and sunlight alone would not provide enough heat to keep water liquid there. But another source of energy turned out to be quietly at work: gravity. Europa's orbit around Jupiter is not perfectly circular. As the moon travels along its slightly stretched path, Jupiter's powerful gravity pulls on it unevenly. This constant tug gently flexes Europa's interior. The process is known as tidal heating. You can imagine it almost like a slow, continuous kneading of the moon's interior. Rock and ice shift slightly with each orbit. Friction builds, and that friction produces heat. Not enough to melt the surface ice, but possibly enough to keep a deep ocean liquid beneath it. In this way, Europa may contain an ocean that has existed for billions of years, hidden beneath ice, shielded from sunlight, moving quietly in darkness. And Europa is not alone. Another small moon, Enceladus, orbiting Saturn, has revealed even more dramatic evidence of hidden oceans. When the Cassini spacecraft explored Saturn's system, it observed something remarkable near Enceladus's south pole. Towering plumes of water vapor were erupting from cracks in the icy surface. These geyser-like jets sprayed material hundreds of kilometers into space. The plumes were made mostly of water vapor and tiny ice particles, but they also contained traces of salts and organic molecules. This discovery strongly suggested that the material was coming from liquid water beneath the surface. In other words, Enceladus too appears to hide a subsurface ocean, an ocean trapped beneath ice, but still active enough to send water spraying into space. And once scientists realized that moons could hide oceans beneath frozen crusts, a quiet shift in perspective began. Oceans, it seemed, did not require open skies or warm sunlight after all. They could exist deep inside small, icy worlds. They could be heated by gravity instead of the sun. They could remain hidden beneath thick shells of ice for billions of years, which raises a gentle possibility. If oceans can exist beneath ice on moons in our own solar system, then perhaps oceans could exist on many other worlds as well, not only beneath ice, but perhaps covering entire planets. Global seas stretching from horizon to horizon, worlds where water is not confined to a few basins or coastlines, but where the entire surface is ocean. And once astronomers began discovering planets around distant stars, that possibility slowly moved from imagination into serious scientific discussion, because some of those distant planets appear to contain extraordinary amounts of water, far more than Earth. And if those worlds exist, their oceans may be unlike anything we have ever seen. Not shallow seas bordered by continents, but deep, endless water, stretching across entire planets beneath unfamiliar skies. Because once astronomers began discovering planets around distant stars, the idea of ocean worlds slowly shifted from speculation into something scientists could begin to examine more carefully. The first confirmed exoplanets, planets orbiting stars beyond our sun, were discovered in the early 1990s. At first, these discoveries were rare and difficult. Astronomers could not see the planets directly. They were simply too small and too dim compared to the stars they orbited. Instead, scientists had to look for subtle effects that planets produced. Sometimes a star would wobble slightly as an unseen planet tugged on it with gravity. Other times, the brightness of a star would dim very slightly as a planet passed in front of it, blocking a tiny portion of its light. These signals were incredibly faint, but as telescopes improved and observations accumulated, astronomers began finding more and more planets around distant stars, then dozens, then hundreds, and eventually thousands. Today, scientists know of several thousand confirmed exoplanets scattered across our region of the galaxy, and they come in a remarkable variety of forms. Some are enormous gas giants larger than Jupiter. Some are small rocky planets similar in size to Earth. Others fall somewhere between, in categories that do not exist in our own solar system. Some planets orbit extremely close to their stars, completing an orbit in just a few days. Others drift far away in colder regions. Some worlds are likely scorching hot, others may be frozen. But among this growing catalog of distant planets, scientists began noticing something intriguing. Certain planets appeared to have densities that suggested they might contain unusually large amounts of water. When astronomers estimate the size of a planet and compare it to its mass, they can often make educated guesses about what the planet is made of. A dense rocky planet will have a certain relationship between its mass and its radius. A gas giant will have a very different one. And planets that appear slightly less dense than solid rock, but heavier than gas worlds, may contain large amounts of water. In some cases, the calculations suggest that water could make up a substantial fraction of the planet's mass, far more than the small percentage that exists on Earth. On our planet, water makes up only a tiny portion of the total mass. The oceans feel enormous to us because they cover most of the surface, but compared to the entire planet, including the mantle and core, Earth's oceans are actually very thin. If you gathered all the water on Earth and shaped it into a single sphere, that sphere would only be about 1,400 kilometers across, small compared to the planet itself. but some exoplanets may contain vastly larger water reservoirs, entire layers of water that extend deep beneath the surface. On such planets, water might not simply fill surface basins. It might form enormous global oceans covering the entire world. Scientists sometimes refer to these hypothetical worlds as ocean planets. A true ocean planet would look very different from Earth. There might be no continents, no mountain ranges rising above sea level, no dry land at all. From horizon to horizon, the surface would simply be water. The sky above it might look different too, depending on the type of star the planet orbits and the nature of its atmosphere. But the surface itself would be an uninterrupted sea. If someone were floating there, hypothetically, they might drift across thousands of kilometers of open water without ever encountering land. Yet, even on Earth, the open ocean is only the surface layer of a much deeper system. And on an ocean planet, the depths could be far greater. On Earth, the deepest trenches reach roughly 11 kilometers below sea level. But on some theoretical ocean worlds, the oceans might extend hundreds of kilometers deep, perhaps even more. At those depths, something unusual begins to happen. Water does not behave exactly the way we expect. Here on Earth, we are familiar with three common states of water: liquid water in rivers and oceans, solid ice when temperatures drop low enough, and water vapor in the atmosphere. But under extreme pressure, water can form many additional structures. The molecules rearrange themselves into crystalline patterns that are quite different from the familiar ice that forms in a freezer. Scientists have identified several of these high-pressure ice phases in laboratory experiments. They have names like Ice 6, Ice 7, and Ice 10. These forms of ice are denser than liquid water, which means that under the right conditions, they can form beneath an ocean rather than floating on top of it. It's a strange idea to picture. A planet where the ocean rests above a layer of solid ice, and beneath that ice, perhaps, lies rock. But physics allows such structures to exist. In an extremely deep ocean, the pressure at the bottom could become so great that water molecules lock into these dense crystalline forms. Even if the water above remains liquid, the result could be a layered world. At the top, a global ocean open to the atmosphere. Below that, a deep region where pressure slowly increases, and deeper still, a thick layer of high-pressure ice. Finally, beneath the ice, the rocky interior of the planet. In this sense, water on such planets might form an entire planetary mantle, a vast region sandwiched between sky and rock. The deeper one travels, the stranger its behavior becomes. And yet, despite these exotic structures, water remains the same familiar molecule. 2 hydrogen atoms, 1 oxygen atom, arranged in countless ways by temperature and pressure. But oceans are not shaped by pressure alone. Gravity also plays a quiet role. On larger planets, stronger gravity pulls everything inward more firmly. This compresses the oceans against the planet's surface. It also increases pressure more rapidly as depth increases. A deeper ocean means heavier water pressing downward, and heavier water means the physics of the lower layers begins to change. On a large ocean world, gravity and pressure together could shape entire planetary interiors made largely of water. But oceans are not isolated systems. They interact constantly with the atmosphere above them. On Earth, evaporation carries water into the air. Clouds form, rain falls, winds push waves across the sea. The atmosphere and ocean move together in an endless cycle. On an ocean planet, That relationship could become even more dramatic. If a planet's surface is almost entirely water, then evaporation could feed enormous atmospheric systems. Clouds might grow thick and widespread. Storm systems might travel across uninterrupted seas. Without continents to interrupt them, winds could circle the entire planet. Weather patterns might persist for long periods, slowly shifting across the globe. And the color of the ocean itself might depend on the type of star shining above it. Stars are not all the same. Some shine bright and white, others glow faintly red. Planets orbiting red dwarf stars, for example, might receive light that is dimmer and redder than the sunlight Earth receives. Under such light, an ocean might appear darker, perhaps reflecting deep crimson tones during sunrise and sunset, or appearing almost black under a faint red sky. These distant oceans would move and reflect light in ways we have never seen. Yet beneath their surfaces, some of the same chemical processes that shape Earth's oceans might still occur, because wherever water meets rock, chemistry begins to unfold. Minerals dissolve slowly into seawater. Chemical gradients form. Energy flows through the system in quiet ways. On Earth, some of the most remarkable examples of this chemistry occur along the seafloor, at places known as hydrothermal vents. These vents form where seawater seeps into cracks in the ocean floor, deep below the surface. That water encounters hot rock heated by Earth's interior. The water becomes superheated and enriched with minerals. Then it rises back upward through the seafloor and flows into the cold ocean water above. From a distance, hydrothermal vents can look like ghostly chimneys rising from the dark ocean floor. Warm, mineral-rich water pours out into the surrounding sea, and around these vents, entire ecosystems flourish. Strange organisms gather there, not because of sunlight, but because of chemical energy. Bacteria use chemical reactions involving minerals to produce energy. Other organisms feed on them. An entire food web forms in complete darkness, and this discovery changed how scientists think about the conditions required for life. For a long time, it was assumed that sunlight was the primary energy source for living systems. But deep beneath Earth's oceans, life had quietly demonstrated another possibility. Life can sometimes thrive using chemical energy alone. And once scientists realized that hydrothermal systems might exist on other ocean worlds, a new idea emerged. If distant planets contain deep oceans, and if those oceans interact with rocky interiors, then similar chemical environments might exist there as well, quietly hidden beneath layers of water, possibly for billions of years. And that thought leads us gently into another question scientists are now exploring. If ocean planets exist around distant stars, how might we detect them from across the vast distances of space? Detecting oceans on distant planets is not a simple task. Even the largest planets orbiting other stars appear impossibly small from our perspective on Earth. They are separated from us by distances measured not in kilometers, but in light years, the distance that light travels in an entire year. Light itself moves incredibly fast, about 300,000 kilometers every second. Yet even at that speed, the light from nearby stars often takes many years to reach us. So, when astronomers study planets around those stars, they are not seeing oceans directly. They cannot watch waves or coastlines or clouds forming above alien seas. Instead, they rely on something quieter and more subtle: light, starlight. Traveling across enormous distances, can carry faint clues about the worlds it encounters along the way. One of the most useful moments for studying an exoplanet occurs when the planet passes directly between its star and our telescopes. This event is called a transit. From our viewpoint, the planet briefly moves across the face of the star, blocking a tiny portion of its light. The dimming is extremely small, often only a fraction of a percent, but sensitive instruments can detect that change by measuring how much light disappears during the transit. Astronomers can estimate the size of the planet. A larger planet blocks more light. A smaller one blocks less. If the planet's orbit repeats regularly, the dimming occurs again and again at predictable intervals. This allows scientists to determine how long the planet takes to travel around its star. From this information, they can estimate how far the planet lies from the star and how warm or cold it might be. But even more information is hidden within the light itself. As the planet crosses the star, a tiny portion of the starlight passes through the planet's atmosphere before reaching our telescopes. And that journey through the atmosphere leaves a faint signature. Different gases absorb different wavelengths of light. Water vapor, methane, carbon dioxide, hydrogen. Each interacts with light in its own distinctive way. When astronomers spread the starlight into a spectrum, like a rainbow of many colors, they can sometimes see small gaps or lines where certain wavelengths have been absorbed. These lines act almost like fingerprints. They tell scientists which molecules are present in the atmosphere of the distant planet. The process is delicate. The signals are faint, but over the past 2 decades, astronomers have begun detecting atmospheric signatures from several exoplanets. And among those signatures, water vapor has occasionally appeared. This does not necessarily mean that oceans exist on the surface. Water vapor could come from many different sources. A hot planet might have steam in its atmosphere. A cold planet might have icy clouds. But in some cases, the presence of water vapor becomes an important clue. Combined with information about the planet's size, mass, and temperature, it can hint that liquid water may exist somewhere in the system, perhaps in clouds, perhaps on the surface, or perhaps hidden beneath thick atmospheres or deep oceans. New telescopes are making these observations more precise. One of the most powerful instruments currently exploring these questions is the James Webb Space Telescope. Webb does not orbit Earth directly. Instead, it travels much farther out to a quiet region of space known as the second Lagrange point, or L2. There, about 1.5 million kilometers from Earth, it can observe the universe without interference from our planet's atmosphere. The telescope carries instruments designed to measure faint infrared light. Infrared wavelengths are especially useful when studying molecules like water. When starlight passes through a planet's atmosphere, water vapor absorbs specific infrared wavelengths. Webb's instruments can detect those subtle patterns with remarkable sensitivity. Already, astronomers have begun studying the atmospheres of several distant planets using this technique. Some of these planets appear to have thick atmospheres rich in hydrogen and other gases. Others show evidence of water vapor mixed into their skies. In a few cases, researchers have suggested that some planets might belong to a category sometimes called Haitian worlds. The name combines 2 ideas: hydrogen, referring to thick hydrogen-rich atmospheres, and ocean, Haitian worlds, if they exist, may be planets somewhat larger than Earth, wrapped in dense atmospheres above global oceans. These atmospheres might help trap heat, allowing liquid water to remain stable, even when the planet orbits a relatively cool star. Some Haitian planets may circle red dwarf stars, small, dim stars that burn slowly and can remain stable for billions of years. In such systems, a planet could orbit fairly close to its star and still maintain moderate temperatures. If oceans exist there, they might remain liquid for immense stretches of time, long enough for complex chemistry to unfold, perhaps even long enough for life to emerge. But scientists approach these possibilities carefully. Detecting water vapor does not prove that oceans exist, and even if oceans are present, life is far from guaranteed. Many conditions must align for biology to develop. Still, the discovery that water appears in so many places across the universe has already reshaped our understanding of planetary systems. For centuries, oceans seemed like something uniquely tied to Earth, a defining feature of our blue planet. But the more we study the cosmos, the more it appears that water is not rare at all. It forms easily, it travels widely, and it gathers into many different environments. Frozen inside comets, locked in the crusts of icy moons, drifting through interstellar clouds, and perhaps on some distant planets, stretching across entire worlds. On those worlds, waves may roll slowly beneath unfamiliar skies. Clouds may form above endless seas. Winds may sweep across horizons with no continents to stop them. And deep below the surface, water may press downward through layers of increasing pressure, eventually forming strange crystalline structures unlike anything we encounter on Earth. If someone could descend through such an ocean, the experience would become stranger the deeper they traveled. At first, the water might feel familiar, cool and dark, much like the deep oceans of Earth. But as the depth increased, pressure would steadily grow. Light would vanish. Temperature and chemistry might begin to shift. Eventually, the water itself might transform. Liquid water above, dense crystalline ice forming below, a layered interior shaped by the quiet physics of pressure and gravity. In that sense, an ocean planet might resemble a vast sphere of water states. Liquid seas above, exotic ice beneath, rock hidden far below. A planetary structure shaped almost entirely by the behavior of a single molecule. And somewhere along the boundary, where water meets rock, chemistry might quietly unfold. Minerals dissolving, energy flowing through chemical reactions. The same processes that, on Earth, support life around hydrothermal vents, tiny organisms gathering around sources of warmth in complete darkness. Life that does not depend on sunlight, life that draws energy from chemistry itself. Whether such systems exist on distant ocean worlds remains unknown, but the possibility has encouraged scientists to search more carefully, to observe more stars, to examine more planetary atmospheres, and to listen closely to the faint signals carried by distant light, because even across light years of space, water leaves subtle traces, tiny patterns in the spectrum of a star, small clues in the motion of a planet, quiet hints that somewhere far away, beneath another sky, an ocean might already be moving. And as our instruments improve, those hints are slowly becoming clearer. With each new discovery, astronomers are reminded of something simple but profound. The universe appears to be a very wet place. Water flows through it in many forms: ice, vapor, liquid, clouds drifting between stars, frozen bodies circling distant suns, hidden seas beneath icy moons. and perhaps countless ocean planets scattered quietly across the galaxy. Worlds where the most familiar substance on Earth gathers into vast and silent seas. And as we continue our slow exploration of the cosmos, those distant oceans invite a gentle kind of curiosity, because every ocean tells a story about the planet that holds it, about gravity, about heat, about chemistry, and about the long, patient processes that shape worlds over billions of years, even when those worlds lie far beyond our reach, even when their oceans will never be seen directly. The light that reaches us from those distant systems carries whispers of their existence, and if we listen carefully enough, we may begin to understand how many quiet oceans are already out there, circling distant stars in the darkness of space. And once you begin to imagine those distant oceans, it becomes natural to wonder what the surface of such a world might actually feel like, not from the perspective of a spacecraft or a telescope, but from the quieter perspective of simply being there. Imagine standing on a small floating platform in the middle of an ocean planet. There is no coastline in any direction, no islands, no continents, just water stretching endlessly toward the horizon. Above you, the sky would depend on the kind of star the planet orbits. If the planet circles a star similar to our sun, the light might appear familiar, bright, white, and warm. But many known exoplanets orbit a different kind of star entirely. Small stars called red dwarfs. These stars are cooler than the sun and glow with a deeper reddish color. Their light is softer and dimmer, but they can shine steadily for extremely long periods of time, sometimes trillions of years. Under the glow of a red dwarf, an ocean might appear very different from Earth's seas. The water might look darker. Reflections on the surface could carry deep red tones, rather than the bright blue-white sparkle we see under our own sun. At sunrise or sunset, the ocean might take on muted shades of crimson or violet as the star sits low on the horizon. Clouds above such an ocean might also behave differently. If a planet's surface is almost entirely covered by water, then evaporation could be constant. Warm sunlight would slowly lift water vapor into the atmosphere. That vapor would cool and condense into clouds. Rain would eventually fall back into the sea. On Earth, continents interrupt this cycle. Land shapes the movement of wind and clouds, but on a planet with no land at all, weather systems could travel enormous distances without interruption. Storms might sweep across entire hemispheres. Winds could circle the planet freely, driven by temperature differences between equator and poles, and the waves beneath those winds might grow very large. On Earth, the longest ocean waves can travel thousands of kilometers across open water before reaching land. On an ocean planet, where no coastline exists to stop them, waves could continue moving across the planet indefinitely. Some might grow into enormous swells, slow rolling walls of water that travel quietly across the entire globe. Yet the surface of the ocean would still represent only the very top of a much deeper system, because beneath the waves, pressure begins to increase almost immediately. Even on Earth, divers notice how quickly the ocean presses inward as they descend. At only 10 meters below the surface, the pressure has already doubled compared to the air above. At 100 meters, the pressure becomes much more intense. At 1,000 meters, sunlight fades away almost completely. And deeper still, the water grows dark and silent. Now imagine extending that descent much farther. Instead of 10 kilometers of depth, imagine an ocean that extends hundreds of kilometers downward. Such depths are difficult to picture. The water above would weigh heavily on every layer below it. Pressure would increase to extraordinary levels. At these depths, water molecules begin to behave in unfamiliar ways. Under enough pressure, water does not always remain a simple liquid. The molecules can reorganize themselves into crystalline structures, dense forms of ice that exist even at relatively warm temperatures. Scientists have created several of these exotic forms in laboratory experiments by compressing water under extreme conditions. Unlike the familiar ice that floats in a glass of water, these high-pressure ices are heavier than liquid water, which means they would sink on a very deep ocean planet. This could produce a surprising arrangement. Liquid water might fill the upper layers of the ocean, but far below, where pressure becomes immense, water could freeze into dense crystalline ice. This ice would form a thick layer beneath the liquid ocean, almost like a hidden floor made of solid water. And below that ice layer, the rocky interior of the planet might begin. In other words, the ocean might not sit directly on rock as it does on Earth. Instead, a deep ocean world might contain several layers: atmosphere above, liquid ocean below, then high-pressure ice, and finally rock, a layered planet built largely from water itself. In such a world, the interaction between water and rock might occur only in limited places, perhaps where heat from the interior pushes upward, or where fractures allow liquid water to reach deeper layers. And those places, if they exist, might resemble some of the most mysterious environments in Earth's own oceans. Hydrothermal vent systems. These vents occur where seawater seeps down into cracks in the ocean floor. Deep beneath the surface, the water encounters rock heated by the planet's interior. Temperatures can rise dramatically. The water becomes rich with dissolved minerals. Then it rises back upward and emerges into the cold ocean water. When it does, the mineral-rich water can form dark, billowing clouds. Over time, the minerals settle and build towering chimney-like structures on the seafloor. From a distance, these vents look almost like underwater geysers, plumes of warm, mineral-laden water rising slowly into the darkness. What makes these places remarkable is not only their geology, it is the life that gathers there. In the deep ocean, far below the reach of sunlight, life has found another way to survive. Bacteria living near hydrothermal vents use chemical reactions involving sulfur and other minerals to generate energy. This process is called chemosynthesis. Instead of relying on sunlight, these organisms rely on chemistry. They form the base of entire ecosystems. Tiny organisms feed on the bacteria. Larger creatures feed on them. Slowly, a complete food web forms around these vents, all in complete darkness, all powered by the chemistry of water and rock. This discovery was one of the most surprising findings of modern ocean exploration. For a long time, scientists assumed that sunlight was essential for life, but hydrothermal vent ecosystems showed that life can sometimes thrive using chemical energy alone. And that realization quietly expanded the range of places where life might exist. Because if life can survive in dark oceans beneath Earth's surface, perhaps it could also survive in oceans on other worlds, even if those oceans lie beneath thick atmospheres, even if sunlight barely reaches their surfaces, even if the water rests beneath kilometers of ice. As long as water exists, and as long as energy flows through chemical reactions, life might find a way to persist. Of course, this remains only a possibility. No life has yet been discovered beyond Earth. Scientists approach the question with patience and caution, but the discovery of hydrothermal ecosystems on our own planet showed that life can appear in places once thought impossible, and that idea gently echoes through the study of ocean worlds. Because if distant planets hold deep oceans, and if those oceans interact with warm, rocky interiors, then somewhere in the darkness beneath those waters, chemistry may be unfolding quietly, minerals dissolving, energy moving through chemical pathways, molecules assembling and rearranging over immense spans of time. The same slow processes that once occurred in Earth's own ancient oceans, processes that eventually led to the first living cells. Whether that story has repeated itself elsewhere remains unknown, but the search for water-rich planets continues to grow more sophisticated. Each year, astronomers discover new worlds orbiting distant stars, some small, some large, some with atmospheres thick with clouds, some with hints of water vapor drifting through their skies. And as telescopes continue to improve, scientists are learning to read those distant atmospheres with increasing clarity. Each spectrum of light carries tiny clues, faint absorption lines where molecules have interacted with starlight, patterns that hint at the composition of alien skies, water vapor, methane, carbon dioxide, hydrogen. Each molecule leaves its own subtle fingerprint, and by studying those patterns carefully, astronomers can begin to imagine what conditions might exist on those faraway planets, whether their surfaces might be hot or cold, whether clouds fill their skies, whether oceans might lie beneath their atmospheres. It is a slow process. No dramatic images of alien seas, no direct views of distant waves, only faint signals carried by light across immense distances. Yet, from those signals, scientists are gradually building a picture of how common water may be in the universe, and that picture continues to grow more interesting with each new discovery. Because the more we observe the cosmos, the more it seems that water is not unusual at all. It forms easily, it travels widely, and wherever planets form, water often follows, which suggests that oceans, in one form or another, may exist in many places throughout the galaxy, some hidden beneath ice, some drifting through atmospheres as vapor, and some, perhaps, stretching across entire planets as silent, global seas, worlds where the surface is nothing but water, where clouds form endlessly above the ocean, where winds travel uninterrupted across the planet, and where the slow chemistry of water and rock may quietly shape the future of that world for billions of years, far away, unseen, yet connected to the same simple molecule that fills our own oceans here on Earth. 2 hydrogen atoms, 1 oxygen atom, arranged together in endless combinations across the universe, a substance so familiar that we rarely pause to consider how extraordinary it really is. And yet, across the galaxy, water may be gathering quietly into oceans beneath distant stars. And once you begin to see water in this wider way, something quietly shifts in perspective. The oceans of Earth stop feeling like an isolated feature of one fortunate planet. Instead, they begin to look like one example of a much larger pattern, water forming wherever conditions allow it, gathering wherever gravity collects it, and slowly shaping the surfaces and interiors of worlds across the galaxy. But the details of those worlds can vary in surprising ways, because planets themselves come in many different sizes. Some are smaller than Earth, others are several times larger, and when a planet grows larger, its gravity changes the behavior of everything on its surface, including its oceans. On a large ocean planet, sometimes called a super-Earth, gravity may be noticeably stronger than what we experience here. That stronger pull presses the ocean more tightly against the planet's surface. Waves might behave slightly differently. Water might feel heavier. Even the movement of currents through the ocean could change. But perhaps the most important effect appears in the deep layers of the ocean. Gravity determines how quickly pressure builds as depth increases. On Earth, pressure rises steadily as you descend. Roughly 1 additional atmosphere of pressure for every 10 meters of depth. At a depth of 1 kilometer, the pressure is already immense. At the deepest trenches, it becomes almost unimaginable. But on a larger planet with deeper oceans, that pressure would rise even more dramatically. Every additional kilometer of water adds enormous weight, pressing downward. And the deeper you go, the more that pressure transforms the behavior of the water itself. Scientists studying the physics of water under extreme conditions have discovered that the molecule is remarkably adaptable. Water can arrange itself into many different crystalline structures depending on pressure and temperature. Under the conditions found on Earth's surface, we are familiar with the most common form of ice, the kind that forms in winter lakes or inside a freezer. That ice floats. It forms delicate crystals. It is lighter than the liquid water beneath it. But under high pressure, water molecules pack together much more tightly. They form dense, compact crystals that behave very differently. These forms of ice are so dense that they sink rather than float, and they can exist at temperatures far warmer than the freezing point we experience at the surface. Laboratory experiments have revealed an entire family of these high-pressure ice structures: Ice 6, Ice 7, Ice 8, each with its own arrangement of molecules, each stable under a different combination of pressure and temperature. These discoveries are important because they help scientists imagine the interiors of deep ocean planets. On such worlds, the ocean may extend downward through many layers. Near the surface, liquid water moves freely, shaped by winds and tides. Deeper down, pressure slowly increases. Eventually, the water molecules are forced into new arrangements. Solid layers begin to form, not because the temperature is extremely cold, but because the pressure has become enormous. The ocean may gradually transition into thick layers of high-pressure ice. It is an unusual idea, ice beneath an ocean, but physics allows it, and on very deep water worlds, it may be inevitable. These layers of dense ice could form a boundary between the liquid ocean above and the rocky interior below. In that sense, the ocean would not sit directly on rock as it does on Earth. Instead, the planet might resemble a vast layered sphere: atmosphere, ocean, high-pressure ice, rock, each layer shaped by gravity, temperature, and chemistry. And yet, even in such unfamiliar conditions, water remains water. The same simple molecule moving through different states, the same substance that forms rivers, rain, clouds, and seas on our own planet. Another quiet factor that shapes ocean worlds is the nature of the star they orbit. Stars come in many sizes and temperatures. Some burn bright and hot, others glow faintly and steadily. The smallest stars, red dwarfs, are especially interesting in the search for ocean planets. Red dwarfs are the most common type of star in our galaxy. They are smaller than the sun and emit less light. but they burn their fuel very slowly. Some may shine for trillions of years, far longer than the expected lifetime of stars like our own, because they are cooler. The region around them where liquid water might exist, sometimes called the habitable zone, lies much closer to the star. A planet orbiting within that region could receive enough warmth to maintain liquid water on its surface, yet it would circle its star much more closely than Earth orbits the Sun. For an ocean planet in such a system, the sky might look very different. The star might appear larger in the sky, but dimmer. Its light would carry a reddish hue. Daylight might feel softer. Sunsets might linger in deep crimson tones, and the ocean beneath that sky might reflect those colors in ways that feel unfamiliar. But the steady warmth from such a star could allow oceans to remain stable for extremely long periods of time, billions of years, perhaps even longer. Time enough for complex chemistry to unfold. Time enough for the slow processes that shape planetary environments. Because oceans are not simply bodies of water, they are dynamic systems. Water circulates, heat moves, minerals dissolve and recombine. On Earth, ocean currents help regulate climate by transporting heat across the globe. Warm water flows from equatorial regions toward the poles. Cold water sinks and moves back toward the tropics. This circulation helps maintain a balance in the planet's temperature. On an ocean planet with no continents to interrupt those currents, the movement of water might become even more global. Currents could circle the planet freely. Heat could move smoothly from warm regions to cooler ones. The entire ocean might function as a vast planetary engine redistributing energy. Above it, clouds might gather in enormous formations. Rain might fall across wide expanses of open sea. Storm systems might travel slowly across hemispheres. Without land to disrupt them, weather patterns might remain stable for long periods. And far below the surface, unseen processes might continue shaping the chemistry of the ocean. Wherever water touches rock, chemical reactions begin. Minerals dissolve, elements mix, energy moves through the system in subtle ways. These interactions between water and rock may be especially important for the possibility of life, because many of the chemical ingredients needed for living systems originate in those environments. On Earth, the earliest forms of life may have emerged in ancient oceans more than 3.5 billion years ago. At that time, the planet looked very different. The continents were smaller. The atmosphere lacked oxygen. Volcanic activity was widespread, but oceans already covered much of the surface. Within those waters, complex chemistry unfolded. Minerals from the seafloor interacted with dissolved molecules in the ocean. Energy flowed through chemical reactions. Over immense stretches of time, simple molecules assembled into more complex ones. Eventually, the first self-replicating systems appeared, tiny living cells, the ancestors of every organism that would later inhabit the planet. Exactly how that transition occurred remains one of science's great mysteries, but many researchers believe that the interaction between water, rock, and chemical energy played a central role, which means that wherever similar environments exist, the possibility of life cannot be entirely ruled out. And that possibility brings scientists back, again and again, to the study of ocean worlds, because water appears to be one of the most common substances in the cosmos. It forms easily, it travels widely, and under the right conditions, it gathers into oceans, some hidden beneath ice, some drifting through atmospheres, some stretching across entire planets. And as astronomers continue searching the sky, they are slowly discovering that planets themselves are far more diverse than we once imagined. Worlds of lava, worlds of gas, worlds of ice, and perhaps many worlds of water, each with its own sky, its own gravity, its own oceans, moving quietly beneath distant stars. And even though we may never visit those worlds directly, the light from their stars carries faint clues about their existence. Tiny patterns, subtle signals, small shifts in brightness, all of them traveling across space to reach our telescopes. And from those signals, scientists are gradually piecing together a quiet picture of the galaxy. A galaxy where oceans may not be rare, a galaxy where water gathers again and again across countless planetary systems, forming seas that move slowly under alien skies, waiting quietly for us to notice that they are there. As scientists continued discovering more exoplanets, another realization slowly began to take shape. Not all ocean worlds would necessarily look the same. Some might have vast open oceans beneath clear skies. Others might be wrapped in thick atmospheres that hide the water far below. And still others might hold their oceans entirely out of sight, sealed beneath layers of ice or high-pressure water. In other words, the idea of an ocean planet may actually include many different kinds of worlds. Some researchers imagine planets where the ocean reaches directly to the surface, stretching across the globe without interruption. But in other cases, the ocean might exist deeper down, beneath a heavy atmosphere composed mostly of hydrogen. These possible worlds are sometimes referred to as Hycean planets. The name blends two ideas together, hydrogen and ocean. On a Hycean world, the atmosphere could be very thick, far denser than the air surrounding Earth. Hydrogen, the lightest element in the universe, might dominate that atmosphere because hydrogen traps heat effectively. Such an atmosphere could act like a warm blanket around the planet. Even if the planet orbits a relatively cool star, the atmosphere could help keep temperatures stable enough for liquid water to exist below. Beneath that thick atmosphere, the surface might be covered entirely by ocean. No continents rising above the water, no exposed land, just a global sea stretching from horizon to horizon. In such an environment, sunlight might filter down through layers of clouds before reaching the water below. The sky might appear hazy or softly glowing rather than sharply blue. The ocean itself might feel calm and heavy under the weight of the thick atmosphere above it. Weather systems could form slowly and move gradually across the planet. Clouds gathering, rain falling, water evaporating and returning again in endless cycles. But what makes Hycean planets especially interesting to scientists is that they may be somewhat easier to detect than smaller Earth-like worlds. Because their atmospheres are thick, the gases within them leave stronger signals in the light passing through them. When a Hycean planet passes in front of its star during a transit, some of the starlight travels through that atmosphere before reaching our telescopes. And within that light, faint patterns appear. These patterns can reveal the presence of certain molecules: water vapor, methane, carbon dioxide, hydrogen. Each molecule interacts with light in its own way. Each leaves a distinctive fingerprint in the spectrum. By studying those fingerprints carefully, astronomers can begin to infer what kinds of gases surround the planet. From there, they can start building models of the planet's possible environment. Is the atmosphere thick or thin? Is the planet hot or cool? Could liquid water exist somewhere within the system? None of these observations provide absolute certainty. but together, they offer valuable clues. The James Webb Space Telescope has already begun examining several planets that may fall into this category. Some appear to have atmospheres rich in hydrogen and water vapor. Others show combinations of gases that suggest complex atmospheric chemistry. Each observation adds a small piece to the puzzle, and slowly, those pieces begin forming a picture of how common water-rich planets might be. Another factor that shapes these distant oceans is the energy flowing through the planet itself. On Earth, part of the heat driving ocean circulation comes from the sun. Sunlight warms the surface water. Currents move that warmth across the planet. But planets also generate internal heat. Deep within Earth's interior, radioactive elements slowly decay. This process releases energy that keeps parts of the mantle warm and drives volcanic activity. In ocean worlds, similar internal heating could play an important role. Heat rising from the interior might warm deep ocean layers. Water circulating through cracks in the seafloor could carry minerals and energy into the surrounding sea. Hydrothermal vents might form along those boundaries, and just as on Earth, those vents could support complex chemical environments, places where water, rock, and heat interact continuously. On Earth, hydrothermal systems produce a variety of chemical gradients. These gradients provide energy that microorganisms can use to sustain themselves. Life around these vents does not rely on sunlight. Instead, it relies on chemical reactions involving sulfur, methane, and other compounds released from the seafloor. This type of ecosystem is one of the most powerful reminders that life can adapt to environments very different from the familiar surface conditions we experience every day. The organisms living there exist in darkness, under immense pressure, surrounded by hot mineral-rich water, yet the ecosystem thrives, which means that similar environments elsewhere in the universe cannot be dismissed too quickly. If a distant ocean planet contains both water and internal heat, hydrothermal systems could potentially exist there as well. Warm, mineral-rich water rising slowly through deep oceans, chemical reactions unfolding in quiet darkness, energy moving through microscopic pathways over vast spans of time. Such environments might allow increasingly complex chemistry to develop. Whether that chemistry ever leads to life remains an open question. Scientists are careful not to assume too much, but they do recognize that oceans provide one of the most stable environments for complex chemistry to persist. Water is an excellent solvent. It allows molecules to move freely. It helps distribute heat evenly, and it supports chemical reactions that might otherwise struggle to occur in dry environments. That is one reason why astronomers are so interested in detecting water on distant planets. Water itself does not guarantee life, but it provides a foundation where many important processes can unfold. And the more astronomers study the galaxy, the more they discover that water appears in many places. It forms in interstellar clouds. It freezes into comets and icy moons. It drifts through atmospheres as vapor, and sometimes it gathers into oceans. Some of those oceans may resemble the seas we know on Earth. Others may be stranger, deeper, darker, more heavily pressurized, their waves moving under unfamiliar skies, their waters reflecting the dim glow of distant stars, and beneath their surfaces, hidden layers of chemistry and physics may be quietly shaping those worlds in ways we are only beginning to imagine. Even though we cannot travel to those oceans, the study of their possible existence has already expanded our understanding of the universe. It has shown that planets are not simple or uniform. They are diverse, complex, each one shaped by gravity, temperature, chemistry, and time. Some worlds may be dry and barren, others may hold vast reservoirs of water, and across the galaxy, oceans may gather again and again, wherever conditions allow them to exist. Worlds where water stretches across entire horizons, where clouds drift slowly across global seas, and where the quiet movement of water continues beneath distant stars. Long before anyone has discovered that those oceans are there, and long after the light from those stars has begun its patient journey toward us across the darkness of space, beyond the atmosphere of an ocean world, another quiet influence continues shaping its seas. Gravity from nearby celestial neighbors. In many planetary systems, planets do not orbit their stars alone. There may be other planets nearby, sometimes larger ones, sometimes smaller, all circling the same star in complex gravitational patterns. These neighboring worlds may appear distant, but gravity reaches across those distances, and over time, that pull can subtly influence a planet's orbit. If the orbit becomes slightly stretched rather than perfectly circular, the distance between the planet and its star changes over the course of each year. When the planet moves closer, it receives a little more warmth. When it drifts farther away, temperatures fall slightly. These gentle variations can shape long-term climate patterns across the planet's oceans. But gravity can also do something else. It can flex the planet itself. You can picture this effect by thinking about Earth's tides. Our moon pulls on Earth's oceans, raising gentle bulges of water that slowly move across the planet. As Earth rotates, the effect is most visible along coastlines where tides rise and fall each day. But something similar happens inside solid planets as well. Rock is not perfectly rigid under the influence of gravity. Entire planetary interiors can flex very slightly. When that flexing repeats again and again, it produces heat. This process is called tidal heating. In our own solar system, tidal heating powers some of the most dramatic geological activity we know. The moon, Io, orbiting Jupiter, experiences intense tidal forces that cause its interior to heat dramatically. As a result, Io hosts hundreds of active volcanoes, but tidal heating can also operate more gently. On ocean worlds, that internal warmth may slowly move upward through the planet's interior. Heat rising from below can warm deep layers of the ocean. Water circulating through cracks in the rocky interior may carry minerals upward. These slow processes can create dynamic environments where water and rock continue interacting over immense spans of time. And once again, we see how oceans become more than just water resting on a planet's surface. They become part of a planetary system connected to gravity, heat, atmosphere, and chemistry. Even the rotation of a planet plays a role. A planet that spins quickly will experience strong Coriolis forces, shaping how winds and currents move across its oceans. On Earth, this rotation helps organize ocean currents into vast circulating systems called gyres. Warm water travels along certain paths, cold water returns along others. These patterns influence weather and climate across entire continents. On a planet covered entirely by ocean, those patterns could become even more pronounced. Currents might circle entire hemispheres without interruption. Heat could travel smoothly from equatorial regions toward the poles. Storms forming above the oceans might follow predictable global paths shaped by these currents. Over time, the ocean itself becomes part of the planet's climate engine, moving heat, balancing temperatures, regulating the atmosphere above. But not all ocean planets may rotate quickly. Some planets orbit so close to their stars that gravity gradually locks their rotation. In these cases, one side of the planet always faces the star. The opposite side remains in permanent darkness. Earth's moon is an example of this phenomenon. The same side of the moon always faces Earth because its rotation has become synchronized with its orbit. If an ocean planet were tidally locked to its star, its climate might be very different. One hemisphere would experience constant daylight. The other would remain under an endless night sky. At first glance, this might seem like a hostile environment. The sunlit side might grow extremely warm. The dark side might become very cold. But if the planet possesses a deep ocean and a thick atmosphere, those systems could redistribute heat. Ocean currents might carry warm water from the bright hemisphere toward the dark one. Winds could move energy through the atmosphere. Clouds might form in particular regions, reflecting some of the incoming starlight. In this way, even a tidally locked ocean world might maintain a relatively stable climate. The ocean itself would help smooth out extreme temperature differences. Water has an enormous capacity to store heat. Once warmed, it releases that heat slowly. This property is one reason Earth's oceans play such an important role in stabilizing our planet's climate. On a deep ocean world, this effect might be even more powerful. Vast volumes of water slowly absorbing and redistributing energy, gently moderating the planet's environment. And if that ocean extends hundreds of kilometers deep, its interior may remain remarkably stable. Far below the surface, sunlight becomes irrelevant. The water grows dark and calm. Temperature changes slowly. Pressure remains constant. These deep layers may persist for millions or billions of years with only gradual changes. Such stability could allow chemical systems to evolve slowly over immense spans of time. Molecules interacting, structures forming, energy flowing through subtle pathways. The same slow chemistry that once unfolded in Earth's ancient oceans. Of course, none of these distant oceans have been seen directly. Astronomers do not yet have the ability to photograph their waves or measure their depths. Instead, they build careful models using the information they can observe: planetary mass, planetary size, orbital distance from the star, atmospheric composition, internal heat. By combining these pieces of information, scientists can estimate what conditions might exist on the planet's surface and within its oceans. Sometimes those models suggest dry, rocky landscapes. Sometimes they suggest thick atmospheres of gas. And sometimes they suggest something more intriguing: deep water worlds, planets where oceans dominate the entire surface. The search for such worlds continues to expand as new telescopes and missions come online. Future observatories may be able to analyze exoplanet atmospheres in even greater detail. They may detect more subtle chemical signals. They may observe smaller planets. They may even identify seasonal changes in distant atmospheres. Each improvement brings us a little closer to understanding the diversity of planetary environments across the galaxy. And each discovery reminds us that the universe is more varied than we once imagined. Planets are not limited to a few familiar types. They come in countless forms, some with lava oceans, some with thick clouds of gas, some with frozen surfaces hiding liquid seas beneath, and some perhaps with endless global oceans reflecting distant stars, worlds where waves travel across planetary horizons, where clouds gather above uninterrupted water, where deep currents move slowly through darkness beneath the surface. And even though these oceans lie far beyond our reach, the idea that they exist connects them to something familiar, because every drop of water in those distant seas follows the same quiet physics as the water on Earth. The same molecular structure, the same ability to dissolve minerals, the same capacity to carry heat and support chemistry. Water does not care whether it lies beneath Earth's sky or beneath the glow of a distant star. Wherever the conditions allow it to gather, it behaves in its patient and adaptable way, flowing, circulating, freezing, evaporating, forming clouds, falling again as rain, a cycle that may repeat across countless worlds scattered throughout the galaxy. And if those distant oceans exist, they may already be moving quietly beneath their alien skies, waves rising and falling, currents circling entire planets, clouds forming above endless seas, all of it unfolding far away, long before we have learned to see those oceans directly, and perhaps continuing long after we finally understand how many of them are there. As astronomers continued studying distant planetary systems, they began noticing another quiet pattern. Water does not only appear on planets themselves, it also appears in many of the small objects that orbit them. Asteroids, comets, icy moons, fragments left behind from the early formation of planetary systems. These small bodies often carry large amounts of frozen water, preserved for billions of years in the cold outer regions around stars. In our own solar system, these icy remnants are everywhere. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are surrounded by dozens of moons, many of which are made largely of ice. Some of these moons are small and irregular. Others are large enough to be worlds in their own right, and several of them appear to hide vast oceans beneath their frozen surfaces. Europa, which we mentioned earlier, is one of the most well-known examples. But another remarkable ocean world lies much farther from the sun, a large moon called Titan. Titan orbits Saturn at a distance where sunlight is weak and temperatures are extremely cold. At first glance, Titan seems like an unlikely place for oceans. Its surface temperature is far below the freezing point of water. In fact, water ice on Titan behaves almost like solid rock. But Titan is unusual for another reason. It possesses a thick atmosphere. Dense clouds of nitrogen and methane surround the moon, forming a hazy orange sky. Beneath that atmosphere, lakes and rivers flow across Titan's surface, but not with water. Instead, these lakes are made of liquid methane and ethane, hydrocarbons that remain liquid at Titan's extremely low temperatures. Rain falls there as methane. Rivers carve channels through icy terrain. Seas gather in broad basins near the poles. In some ways, Titan resembles a strange mirror of Earth, a world with weather, rivers, clouds, and seas, but operating under completely different chemistry. And yet, beneath Titan's frozen outer crust, scientists suspect that something very familiar may exist. A hidden ocean of liquid water, deep below the icy shell. The evidence comes from careful measurements of the moon's gravity and rotation. These observations suggest that Titan's outer layers may be floating above a deep internal ocean. If this ocean exists, it could be extremely large, perhaps hundreds of kilometers deep. Above it, the icy crust remains frozen solid. Below it, the rocky interior of Titan continues downward. Between those layers, the ocean rests quietly, sealed beneath ice, It is another reminder that oceans do not always appear where we might first expect them. Sometimes they lie beneath frozen surfaces, sometimes beneath thick atmospheres, sometimes beneath kilometers of rock and ice. And because of this, scientists have begun to suspect that ocean worlds may be extremely common, not only among planets, but among moons as well. If that is true, then the number of oceans in the universe could be far larger than the number of planets with surface seas like Earth. Hidden oceans might exist wherever water, heat, and pressure combine in the right way. And in some cases, those oceans may remain stable for incredibly long periods of time, billions of years, time enough for chemistry to slowly unfold, time enough for complex systems to emerge. But even when oceans exist, they do not remain still. Water is always moving. Currents circulate, temperatures shift, chemical gradients form and fade. On Earth, the oceans act almost like a living system, constantly redistributing heat and nutrients around the planet. Cold water sinks near the poles and moves slowly along the ocean floor. Warm water rises in other regions. Currents carry energy across vast distances. These patterns help regulate the climate of the entire planet. Without them, Earth's environment would be far less stable. On an ocean planet with no continents, this circulation might become even more global. Water could move freely across the entire surface of the world. Massive currents might wrap around the planet like slow-moving rivers within the sea. Heat absorbed near the equator could gradually travel toward cooler regions. Over time, the ocean itself would become the primary mechanism regulating the planet's climate. And because water holds heat so effectively, changes would often occur slowly. Temperatures shifting gradually over long periods, storm systems forming and fading, clouds gathering above warm ocean regions, all of it unfolding at a pace that feels almost geological in its patience. Yet, beneath the surface, much faster changes may occur. Chemical reactions, mineral exchanges, microscopic life, if it exists, reproducing and evolving. The deep ocean on Earth contains countless microorganisms. Many of them have never been seen or studied. Some survive in extreme conditions of pressure, darkness, and temperature. They draw energy from chemical reactions involving sulfur, iron, methane, and hydrogen. These organisms remind scientists that life is remarkably adaptable. It does not require sunlight in every environment. It can survive where energy flows through chemical pathways instead. And that insight continues to influence how scientists think about the potential for life beyond Earth. Because if deep ocean chemistry can support ecosystems here, perhaps similar environments could exist elsewhere, deep beneath the surfaces of distant planets, within hidden oceans sealed under ice, or in global seas stretching across alien worlds. None of these possibilities have yet been confirmed. The search is still in its early stages, but each new observation adds another piece to the puzzle. A new exoplanet discovered, a new atmospheric signature detected, a new moon revealed to contain subsurface water. Slowly, carefully, scientists are learning that water may be one of the most persistent substances in the universe. It forms easily, it moves freely, it adapts to a wide range of environments, and wherever planets form, water often appears somewhere in the system, sometimes frozen, sometimes drifting as vapor, sometimes gathered into lakes, rivers, or oceans, and sometimes hidden deep beneath surfaces where sunlight never reaches. In that sense, Earth's oceans may be part of a much larger cosmic story, one chapter in a long narrative written in water. a story unfolding across billions of planets, moons, and icy bodies scattered throughout the galaxy. Most of those oceans will never be seen directly. They lie too far away, their light too faint, their waves too distant. But the quiet signals carried by starlight continue reaching our telescopes. And within those signals, scientists can sometimes glimpse hints of distant water worlds, small clues that somewhere far away, beneath unfamiliar skies, another ocean may already be moving. And when you pause for a moment to think about all of these different worlds, something gently surprising begins to emerge. Water does not belong to one single kind of planet. It appears in many forms, across many environments, shaped by temperature, pressure, gravity, and time. On Earth, water gathers into oceans beneath an open sky. On Europa, it may lie hidden beneath thick ice. On Titan, it may rest beneath a frozen crust, while methane rivers flow above. And on distant exoplanets, water may form oceans so deep and extensive that they reshape the entire structure of the planet itself. In this way, water becomes more than just a familiar substance. It becomes a quiet architect of worlds, because wherever large amounts of water gather, the behavior of that water begins influencing the planet around it. Water stores heat. It moves energy from one region to another. It dissolves minerals and carries them across long distances. It shapes atmospheres through evaporation and condensation. And over time, these processes gradually alter the environment of the planet. Even small changes in water circulation can affect global climate. On Earth, for example, the movement of warm water across the Atlantic Ocean helps keep parts of Europe much warmer than they would otherwise be. This circulation, sometimes called the Atlantic Meridional Overturning Circulation, carries heat from tropical regions toward higher latitudes. If those currents were to weaken significantly, temperatures across large areas of the planet could change. The ocean is not simply water resting quietly in place. It is a dynamic system constantly exchanging heat, gases, and nutrients with the atmosphere above. And on a planet covered entirely by ocean, that system would become even more dominant. Without continents to interrupt the flow of water, currents might move more smoothly across the planet. Large-scale circulation patterns could form that wrap around the entire globe. Warm water rising near equatorial regions, cooler water sinking in other places. These movements would slowly redistribute energy throughout the ocean. Above the surface, the atmosphere would respond. Warm regions might generate towering cloud systems. Rainfall could fall steadily over vast areas of open sea. Storms might drift slowly across hemispheres, fueled by the energy stored in the ocean below. But even deeper layers of the ocean would remain largely insulated from these surface changes. Hundreds of kilometers beneath the waves, sunlight would have no influence at all. There, the ocean would become a world of quiet stability. The temperature would change only gradually. Currents would move slowly through darkness. Pressure would remain immense and constant. In such environments, chemical reactions between water and rock might proceed steadily for millions or even billions of years. Minerals dissolving, compounds forming, energy flowing through subtle pathways. The deeper we look into Earth's oceans, the more we discover how rich these environments can be. Hydrothermal vent systems host entire communities of organisms that survive without sunlight. Some bacteria draw energy from hydrogen sulfide. Others use methane or iron. These chemical reactions provide enough energy to support complex ecosystems. Creatures cluster around the vents: tube worms, crustaceans, strange fish adapted to life in darkness, all of them depending on the energy released where water meets hot rock. When scientists first discovered these ecosystems in the late 20th century, the finding was almost startling. Until then, most biological systems known to science depended on sunlight in one way or another. But here, deep beneath the ocean's surface, life was thriving in complete darkness, powered not by light, but by chemistry. This discovery reshaped how scientists think about the potential habitability of other worlds. If life can exist in such environments here, then similar environments elsewhere might also support living systems. That possibility is one reason why ocean worlds receive so much attention in planetary science. Because water is not only common, it is also extraordinarily good at supporting chemical complexity. Water molecules are polar. They carry slight electrical charges that allow them to interact with many other molecules. This property makes water an excellent solvent. It allows salts, minerals, and organic molecules to dissolve and mix together. Within that liquid environment, chemical reactions can occur more easily. Molecules collide, bonds break and reform. Structures assemble and rearrange. Given enough time, such chemistry can become very elaborate. On Earth, these processes eventually led to the emergence of life. Exactly how that happened remains one of the great mysteries of science. But the presence of liquid water appears to have been an important part of the story, because water allows molecules to move freely and interact in ways that dry environments do not. And across the universe, wherever water gathers into stable environments, the possibility of complex chemistry arises again. Perhaps only chemistry, perhaps, in rare cases, something more. Scientists approach these questions carefully. Detecting water on a distant planet does not mean life exists there. Even a large ocean does not guarantee that biology has developed. Many additional factors must align: temperature, chemical composition, energy sources, stability over long periods. All of these influence whether life can emerge. But the discovery that water may be widespread throughout the cosmos has already changed the way we view the universe. It suggests that the basic ingredients for complex chemistry may be present in many places: planets and moons, where oceans persist for billions of years, environments where energy flows through water and rock, systems where molecules have time to interact and evolve. And even if life never appears in most of those places, the chemistry itself may still unfold in fascinating ways. Minerals forming intricate crystalline structures, chemical cycles circulating through oceans and atmospheres, planetary climates shaped by the movement of water across entire worlds. In that sense, oceans do not need to contain life to be remarkable. The mere existence of such vast bodies of water on distant planets is itself a quiet wonder, because oceans represent stability, persistence, time. Water moves slowly through cycles that can last millions of years, evaporating, condensing, freezing, melting, flowing again. Across the universe, those cycles may be repeating on countless worlds: clouds rising above alien seas, rain falling into oceans that have never known a shoreline, currents drifting beneath skies illuminated by unfamiliar stars, all of it unfolding quietly in the vast darkness between the stars. And here, on Earth, When we stand beside the ocean and watch the waves moving slowly toward the shore, we are seeing one small example of that larger pattern. Water moving across a planet, energy flowing through a system that has been active for billions of years. A reminder that something as familiar as the ocean is part of a much wider cosmic story, one that extends far beyond our own planet, far beyond our solar system, out into a galaxy where distant oceans may already be moving quietly beneath alien skies. As the search for distant oceans continues, astronomers are gradually learning that the story of water in the universe is not a simple one. Water does not appear in the same way everywhere. Sometimes it gathers into shallow seas. Sometimes it hides beneath ice. Sometimes it forms enormous atmospheric clouds drifting above planets. And sometimes it may fill entire planetary layers that extend hundreds of kilometers beneath the surface. Each environment changes how water behaves. Temperature, gravity, and pressure reshape its movement and structure in quiet but powerful ways. One particularly interesting factor is how water interacts with planetary atmospheres over very long periods of time. On Earth, the ocean and the atmosphere exist in a continuous conversation. Water evaporates from the surface of the sea and rises into the air as vapor. As the vapor cools, it condenses into clouds. Eventually, rain falls and returns that water back to the ocean. This cycle, evaporation, condensation, and precipitation, repeats endlessly. It is one of the most familiar natural processes on our planet, but on an ocean world, where the entire surface is water, this cycle could become even more dominant. Evaporation might occur across nearly the entire planet. Cloud systems could grow extremely large. Rain might fall over enormous stretches of ocean without interruption. Without continents to disrupt atmospheric circulation, winds might move clouds across vast distances. Some regions might experience steady rainfall for long periods. Others might remain relatively clear. Over time, the atmosphere and ocean would adjust to each other, gradually reaching a kind of balance. The ocean providing moisture and heat, the atmosphere redistributing that energy through winds and clouds. On Earth, the presence of continents creates boundaries that shape weather systems. Mountain ranges redirect winds. Land surfaces heat and cool more quickly than oceans. All of these factors influence how storms form and move. But on a planet with no land at all, the atmosphere might behave more smoothly. Storms might develop over warm ocean regions and travel long distances without interruption. Weather systems could grow large and persistent, circling the planet over weeks or months. Even the color of the sky might differ from what we see on Earth. Atmospheric composition affects how light scatters through the air. Our own sky appears blue because molecules in Earth's atmosphere scatter shorter wavelengths of sunlight. But an atmosphere rich in different gases might scatter light differently. Under some conditions, the sky above an ocean world might appear hazy or softly tinted. Sunsets might glow in unusual colors. Clouds might reflect light in ways unfamiliar to our eyes. These subtle differences remind us that each ocean world would possess its own character, its own climate, its own rhythm of wind and water. Yet beneath the surface, some processes would remain surprisingly familiar, because wherever water touches rock, chemical exchanges begin. Minerals dissolve slowly into the ocean. Elements mix and react. Heat from the planet's interior may rise through cracks and fractures in the seafloor. In some places, That heat may create hydrothermal systems similar to those found in Earth's deep oceans. Warm, mineral-rich water emerging slowly from beneath the seabed, carrying dissolved elements upward into the surrounding water. These environments can become chemically rich. Gradients of temperature and chemistry form where hot fluids mix with colder ocean water. And wherever such gradients exist, energy flows through the system. On Earth, microorganisms take advantage of those energy flows. They use chemical reactions to build organic molecules and sustain themselves. Over time, entire ecosystems grow around these chemical energy sources. Whether similar ecosystems exist elsewhere remains unknown, but the presence of water and chemical energy provides a foundation where complex chemistry can unfold. Another factor influencing ocean worlds is the slow movement of tectonic activity within a planet. On Earth, the crust is divided into plates that move gradually across the surface. These movements create mountain ranges, earthquakes, and volcanic activity. They also play an important role in recycling minerals between the ocean and the interior of the planet. Subduction zones carry oceanic crust downward into the mantle. Volcanoes release gases and minerals back into the atmosphere and ocean. This slow geological cycle helps regulate Earth's long-term climate. On ocean planets, tectonic processes might operate differently. Without continents, the crust could form a continuous shell beneath the ocean. Heat from the interior might still drive movement within that shell. Volcanic activity could occur along fractures beneath the sea. Underwater volcanoes might release minerals and gases into the surrounding water. In some regions, new crust might slowly form, while older crust sinks deeper into the planet. These geological cycles would continue shaping the chemistry of the ocean over immense stretches of time. And through all of this activity, the ocean itself remains a stabilizing presence. Water absorbs heat slowly. It releases heat slowly. This property allows oceans to moderate temperature changes across the planet. If the star grows slightly brighter over time, the ocean may absorb part of that additional energy. If the planet cools, the stored heat in the ocean may help prevent rapid freezing. This buffering effect is one reason oceans are considered such important components of planetary habitability. They create environments where conditions can remain relatively stable over long periods. Stability gives chemistry time to unfold. It allows complex systems to develop gradually, and in rare cases, it may allow life to emerge. But even in the absence of life, the presence of oceans alone can shape the evolution of a planet. Over millions of years, waves erode rock. Minerals circulate through water. Atmospheric gases dissolve into the ocean and later return to the air. Planetary climates evolve slowly as water cycles through different states: liquid, vapor, ice, each state interacting with gravity, sunlight, and chemistry. Across the galaxy, these same processes may be occurring again and again. On distant planets orbiting faint red stars, on icy moons circling gas giants, on water-rich worlds wrapped in thick atmospheres. Most of those places will remain forever beyond human reach, their oceans too distant to explore directly. Yet the light from their stars carries subtle traces of their existence, spectral fingerprints of water vapor, small variations in brightness as planets pass in front of their stars, tiny clues hidden in the signals received by telescopes. From those clues, astronomers gradually piece together a picture of the wider universe, a universe where water is abundant, where oceans may exist on worlds we have never seen, and where the quiet physics of water its ability to flow, dissolve, freeze, and circulate continues shaping planets across the vast expanse of the galaxy. In that sense, the oceans we know on Earth are not isolated. They are part of a much larger family of waters that drift through space as vapor, waters locked inside icy moons, waters gathered into global seas beneath alien skies, all of them following the same simple chemistry: 2 hydrogen atoms, 1 oxygen atom, a small molecule with an extraordinary ability to shape worlds. And when scientists step back and look at the wider picture, something quietly remarkable begins to appear. Water is not only common, it is persistent. Across the universe, water seems to endure through enormous changes in environment and time. It freezes into ice when temperatures fall. It turns to vapor when warmth rises. It condenses again when conditions shift. And through all of those transformations, the molecule itself remains stable. 2 hydrogen atoms, 1 oxygen atom, a simple structure that has survived the entire history of the universe. Hydrogen formed very early, within minutes of the Big Bang. Oxygen formed much later inside the cores of stars. When those stars aged and eventually died, they released oxygen into space, enriching the surrounding clouds of gas and dust. Within those clouds, hydrogen and oxygen eventually met, and when they did, water began to appear. It formed as vapor. It froze onto tiny grains of cosmic dust. It drifted through interstellar clouds where new stars and planets were slowly taking shape. Over time, some of that water became trapped inside the material that formed planets. Some remained frozen in distant icy bodies. Some evaporated in joined planetary atmospheres, and some gathered into oceans. This quiet cycle of formation, transformation, and movement continues even today. Across the galaxy, new stars are still forming inside vast molecular clouds. Around those young stars, disks of dust and gas spin slowly. Within those disks, tiny particles collide and grow. Pebbles become rocks, rocks become planetesimals, and over millions of years, planets emerge. If water ice is present within those disks, and astronomers have observed that it often is, then some of that water becomes part of the planets that form there, which means that the oceans of distant worlds may begin their story long before the planets themselves are fully assembled. Water drifting through interstellar space, becoming trapped in icy grains, joining the swirling disks around newborn stars, and eventually gathering into oceans on newly formed planets. When we think about oceans on Earth, it is easy to imagine them as ancient features of our own planet alone. But in reality, they are part of a much longer cosmic history, a history that begins in the cold darkness between the stars and continues across billions of years as planets form, evolve, and sometimes gather water into seas. This realization has quietly changed how astronomers think about the universe. For much of human history, Earth seemed uniquely suited for oceans, a rare world with the right balance of temperature and conditions. But the more scientists observe other planetary systems, the more they see that water appears in many different environments. Some planets may be too hot for oceans, others may be too cold. Some may have lost their water over time, but many worlds appear capable of holding water in one form or another. And when water remains stable for long periods, oceans can emerge, sometimes shallow, sometimes deep, sometimes hidden beneath ice or thick atmospheres. and sometimes stretching across entire planets, each of those oceans becomes part of the environment of its world. It shapes the climate, it influences the chemistry, it interacts with the planet's interior and atmosphere. Over time, these interactions can change the entire character of the planet. A dry world may remain barren. A water-rich world may develop clouds, storms, and currents. In some rare cases, chemistry within those oceans may even become complex enough to support living systems. But even when life does not appear, the oceans themselves remain remarkable, because oceans represent a kind of balance. They store energy from stars. They redistribute that energy across the planet. They provide a medium where chemistry can unfold, and they persist through immense spans of time. The oceans of Earth have existed for billions of years. They have witnessed the rise and fall of countless species. They have shaped the atmosphere and climate of the planet. And throughout that time, the water itself has continued cycling endlessly through the environment, evaporating into clouds, falling again as rain, freezing into glaciers, melting into rivers, returning to the sea. Across the galaxy, similar cycles may be unfolding on other worlds. Clouds rising above alien seas, rain falling into oceans that have never known a shoreline, currents drifting slowly beneath unfamiliar constellations, all of it happening quietly, far beyond our sight. When astronomers search for ocean planets, they are not only looking for water, they are also looking for the story of how planets evolve. Water carries clues about a planet's formation, about the materials that built it, about the processes shaping its atmosphere and interior. Even the absence of water can reveal something about the history of a world. Perhaps the planet formed in a dry region of its system. Perhaps its atmosphere escaped into space. Perhaps its star grew brighter and slowly evaporated its oceans. Every planet tells a story, and water often appears somewhere within that story. Sometimes as ice, sometimes as vapor, sometimes as oceans, which brings us back to the quiet realization that has gradually emerged over the past few decades. The universe may be filled with oceans, some visible, some hidden, some frozen beneath ice, some stretching across entire planets, each one moving slowly beneath the gravity of its star, each one shaped by the same simple molecule that fills the seas of Earth. 2 hydrogen atoms, 1 oxygen atom, a structure so small and familiar that it fits easily within a single drop of water. And yet, when multiplied across entire planets, that tiny molecule becomes something immense. Vast global oceans, planetary weather systems, deep currents circulating through darkness, all emerging from the quiet behavior of one of the universe's simplest chemical combinations. And somewhere out there, beyond the stars we see at night, those oceans may already be moving. Clouds forming above their surfaces, rain falling into seas that no human has ever seen, waves rising and falling beneath skies illuminated by distant suns, all of it unfolding patiently across the immense timescales of the cosmos. Long before we notice those worlds, and long after the light from their stars has begun its long journey toward us across the silent depths of space, and as our understanding of these distant oceans slowly grows, another quiet realization begins to emerge. Not all oceans need to exist on the surface of a planet. Some may lie entirely out of sight, hidden beneath thick layers of ice or deep atmospheres, sealed away from the open sky. In our own solar system, this idea has already transformed the way scientists think about where water might exist. For a long time, the search for liquid water focused mostly on the surfaces of planets, places where sunlight might warm lakes, rivers, or seas. But the discoveries on moons like Europa and Enceladus revealed something surprising. Liquid water can exist far below the surface, protected from the cold of space by thick shells of ice. These shells act almost like insulating blankets. They trap heat rising from the interior of the moon. They shield the ocean beneath from the harsh environment above, and over immense spans of time, they allow liquid water to remain stable, even in places where the surface is frozen solid. If you could stand on Europa's surface, for example, you would see an endless frozen landscape. The ground beneath your feet would be ice. The temperature would be extremely cold. Above you, Jupiter would loom enormous in the sky, yet far below that frozen crust, scientists believe an ocean may be moving slowly in darkness. An ocean perhaps deeper than all the seas on Earth combined. The same may be true for several other icy moons: Enceladus, Ganymede, Callisto, Titan. Each of them may hide oceans beneath frozen surfaces, and if that pattern holds true in other planetary systems, the number of ocean worlds could be far greater than the number of planets with open seas. Some of those oceans may remain hidden forever, sealed beneath ice for billions of years. Others may occasionally reveal themselves through small clues. On Enceladus, for example, fractures in the ice allow plumes of water vapor to escape into space. Those plumes rise hundreds of kilometers above the moon's surface before falling back again as tiny, icy particles. When spacecraft passed through those plumes, instruments detected water vapor, salts, and organic molecules, evidence suggesting that the ocean below interacts with the moon's rocky interior, even though the ocean itself remains unseen. The material rising through the cracks offers a glimpse into what lies beneath. It is almost as if the moon is breathing small traces of its hidden ocean into space. Similar processes may occur on other worlds. Cracks opening and closing slowly, water rising through fractures, frozen particles drifting outward before settling again on the surface. Small signals that hint at vast oceans hidden below. When astronomers think about distant planetary systems, they now consider these possibilities carefully. Because an ocean does not have to be visible to exist. A planet or moon might appear dry and frozen from a distance, yet beneath its surface, liquid water could still be present, protected by layers of rock or ice, warmed by the slow release of internal heat, moving quietly in darkness. In fact, some researchers believe that subsurface oceans could be among the most common liquid water environments in the galaxy. Surface oceans require a delicate balance of conditions. The planet must be warm enough for water to remain liquid, but not so warm that the water evaporates away. It must also retain an atmosphere capable of maintaining pressure. Subsurface oceans, however, can exist in colder environments. As long as internal heat remains available and the surface layers provide insulation, liquid water can persist far below. This means that ocean environments might appear on worlds that orbit far from their stars, worlds that receive very little sunlight, icy planets drifting in cold regions of planetary systems, moons orbiting giant planets, even rogue planets, planets that have been ejected from their systems and wander through interstellar space. Some scientists have proposed that such rogue worlds might still possess subsurface oceans. Beneath thick layers of ice, internal heat could maintain pockets of liquid water for extremely long periods. From the outside, such a planet would appear dark and frozen, but beneath its crust, an ocean might still exist, a quiet sea hidden beneath kilometers of ice. These hidden oceans remind us that water is remarkably adaptable. It does not require perfect surface conditions. It can survive in darkness, under pressure, protected beneath layers of rock or ice. And because water remains liquid across a wide range of temperatures and pressures, it can persist in many environments where other liquids would freeze or evaporate. This adaptability is one reason water is so important in planetary science. It shapes the evolution of worlds. It influences geology and atmosphere. And it provides an environment where complex chemistry can occur. Across the universe, the story of water continues unfolding in countless places. Interstellar clouds forming new stars, comets drifting through planetary systems, icy moons circling giant planets, exoplanets wrapped in global seas, hidden oceans sealed beneath frozen crusts, each one part of the same quiet cycle. Water forming, moving, freezing, melting, evaporating, condensing, a substance that flows easily between different states while remaining chemically stable. And when astronomers look up at the night sky, they are not only seeing distant stars, they are also seeing the places where that cycle may already be underway, where water molecules drifting through space have gathered into clouds, planets, and oceans, where distant seas may be moving beneath unfamiliar skies, their waves unseen, their currents unknown, yet following the same simple physics that governs the oceans here on Earth. Water moving slowly under gravity, heat rising from planetary interiors, clouds forming and dissolving above global seas, all of it happening quietly across the vast distances of the galaxy. And as our instruments grow more sensitive, the faint signals carried by distant starlight continue revealing small hints of those worlds, tiny spectral fingerprints, subtle dimming of distant stars, clues that somewhere far away, beneath layers of atmosphere or ice, an ocean might already be flowing. An ocean formed from the same simple molecule that fills the seas of our own planet. A molecule that began its journey billions of years ago in the hearts of ancient stars, and that continues, even now, shaping worlds across the universe. As astronomers gather more of these faint signals from distant planetary systems, a different kind of question begins to form. Not only where oceans exist, but how long they can last, because the story of a planet is always changing. Stars slowly grow brighter over time. Planetary atmospheres can thicken, thin, or escape into space. Internal heat gradually fades as a planet ages. All of these slow processes influence whether an ocean can remain stable. On Earth, the oceans have persisted for more than 3 billion years. That length of time is almost difficult to imagine. 3 billion years of waves moving across the surface. 3 billion years of clouds rising and falling. 3 billion years of currents circulating through the depths. But Earth's oceans did not remain identical during all that time. The early oceans were likely warmer. The atmosphere contained different gases. The continents were arranged in different positions. Yet, despite those changes, the oceans themselves endured. And that endurance reveals something important about water. Water has an unusual ability to stabilize environments. Because it absorbs heat slowly and releases it slowly, large bodies of water can moderate dramatic temperature swings. During warm periods, oceans absorb excess energy. During cooler periods, they release stored warmth back into the atmosphere. This buffering effect helps maintain conditions where liquid water can persist. And that same stabilizing property may apply to ocean planets as well. If a world possesses an enormous global ocean, the water itself may help regulate the planet's long-term climate, even if the star gradually brightens over millions of years. The ocean may absorb part of that change. Temperatures may shift slowly rather than suddenly. Clouds may adjust. Circulation patterns may reorganize. But the ocean continues moving, storing energy, redistributing it across the planet. Of course, stability is not guaranteed. Some planets may lose their oceans entirely. If a planet orbits too close to its star, heat can cause water to evaporate rapidly. Water vapor rises high into the atmosphere, where sunlight can break the molecules apart. Hydrogen escapes into space. Oxygen reacts with surface rocks. Over long periods, the planet may gradually lose its water. Something like this may have happened to Venus long ago. Venus may have possessed shallow oceans or large bodies of water, but as the sun's energy warmed the planet, evaporation increased. The atmosphere grew thicker. Heat became trapped more effectively, and eventually, the planet entered a runaway greenhouse state. Today, Venus is an extremely hot world with thick clouds of carbon dioxide and sulfuric acid. If oceans once existed there, they are long gone. This example reminds scientists that oceans are not permanent features. They depend on a delicate balance between temperature, atmospheric pressure, gravity, and chemistry. When those conditions shift too far, oceans can disappear, but the opposite can also happen. Some worlds may begin cold and frozen, only to warm slowly as internal heat rises or atmospheric changes occur. Ice may melt. Subsurface oceans may emerge. Liquid water may appear where none existed before. Planetary history is rarely simple. Instead, it unfolds gradually over immense stretches of time. Planets warm and cool, atmospheres evolve, water moves between ice, vapor, and liquid. Across the galaxy, many worlds are probably experiencing these transitions right now, some losing oceans, some gaining them, some maintaining them quietly for billions of years. And because these processes occur slowly, they are difficult for us to observe directly. A planet's climate may change over millions of years, far longer than a human lifetime. Yet astronomers can still glimpse hints of these changes by studying the atmospheres of distant worlds. When a planet passes in front of its star, a small fraction of starlight filters through its atmosphere. That light carries subtle chemical signatures. Different gases absorb different wavelengths of light. By analyzing these patterns, scientists can identify molecules present in the atmosphere: water vapor, carbon dioxide, methane, oxygen. Each molecule leaves its own faint imprint. These spectral fingerprints allow astronomers to begin building a picture of what distant atmospheres might contain. If water vapor appears in large quantities, it may suggest that oceans exist below. If clouds form high in the atmosphere, they may influence how heat is distributed across the planet. Even small clues can reveal surprising details about distant environments. Telescopes like the James Webb Space Telescope are now capable of measuring some of these signals with remarkable precision. By observing multiple planets and comparing their atmospheric compositions, scientists are gradually learning how common water-rich worlds might be. Some early observations already hint at planets with thick atmospheres containing water vapor. Others appear to possess conditions where liquid water could exist at the surface. And although the data is still limited, each discovery adds another small piece to a much larger puzzle. A puzzle that stretches across the entire galaxy, because every star we see in the night sky may host its own collection of planets, some rocky, some gaseous, some frozen, and some perhaps covered by oceans. If even a small fraction of those worlds contain stable oceans, then the number of water-rich planets in our galaxy alone could be enormous. Thousands, perhaps millions, each one circling its own distant sun, each one shaped by gravity, chemistry, and time. And across all of those worlds, water would continue its quiet work, circulating through atmospheres, flowing across planetary surfaces, moving through hidden oceans beneath layers of ice. A simple molecule repeating the same patterns again and again across the vast architecture of the cosmos. 2 hydrogen atoms, 1 oxygen atom, a structure so small it can exist within a single droplet, and yet capable of forming oceans that span entire planets, oceans that rise and fall with tides, that exchange heat with distant stars, that slowly reshape the worlds they rest upon. When astronomers search for ocean planets, they are not only looking for water, they are looking for these quiet planetary systems in motion, worlds where chemistry, climate, and gravity combine to produce something stable enough for oceans to endure. Places where water may continue flowing quietly through cycles that last longer than human civilizations. And somewhere out there, beneath unfamiliar constellations, those cycles are likely already underway. Clouds drifting above distant seas, rain falling into oceans that have never known a shoreline, currents circling entire planets beneath alien skies, all unfolding slowly in the immense calm of the galaxy. Even with all that astronomers have learned, there is still a gentle humility in the way scientists speak about these distant oceans, because, for now, they remain unseen. No spacecraft has yet traveled to an exoplanet ocean. No camera has captured the surface of a sea circling another star. Everything we know about these worlds arrives to us in quiet, indirect ways. A faint dimming of starlight as a planet passes in front of its star. A tiny shift in the star's motion as gravity reveals the presence of an orbiting world. A delicate change in the spectrum of light, hinting that certain molecules may be present in the planet's atmosphere. From these small signals, astronomers reconstruct entire planetary systems. They estimate the size of the planet, its mass, its distance from its star, its temperature, its atmosphere, and from those pieces, they begin imagining what conditions might exist on its surface. Sometimes the models suggest dry deserts of rock, sometimes thick atmospheres of gas, and sometimes the possibility of oceans. But the language of science remains careful. Astronomers often say that a planet could host oceans, or that conditions may allow liquid water to exist, because until more direct observations become possible, these distant seas remain possibilities rather than confirmed landscapes. And yet, even these possibilities carry a quiet sense of wonder, because only a few decades ago, scientists did not know whether planets existed around other stars at all. The first confirmed exoplanets were discovered in the 1990s. Since then, thousands of worlds have been identified, some larger than Jupiter, some smaller than Earth, some orbiting extremely close to their stars, others drifting much farther away. Each discovery revealed that planetary systems are common, and once planets became common, the question of water followed naturally. If planets are everywhere, then the environments that allow water may also be widespread. Today, astronomers continue expanding the search. New telescopes are being planned and built with even greater sensitivity. Some will be able to observe planets directly, separating their faint light from the glow of their parent stars. Others will analyze planetary atmospheres with extraordinary precision. Over time, these instruments may allow scientists to detect more subtle signals, perhaps even clouds forming in distant atmospheres, or seasonal changes in planetary climates, slow hints that oceans might be shaping the world below. But even before those discoveries arrive, the idea of ocean planets already changes how we think about the universe. For most of human history, Earth seemed like a singular place, a rare world with oceans, clouds, rain, and life. But as our knowledge expands, it becomes increasingly clear that many of the ingredients that shape Earth may exist elsewhere as well. Gravity, rock, atmospheres, and water, each one following the same physical laws across the cosmos, which means that when we imagine distant oceans, we are not imagining something entirely unfamiliar. The physics of those oceans would be the same as the physics of the sea here on Earth. Water would still flow downhill, waves would still rise and fall under the pull of gravity, heat would still move slowly through deep currents, clouds would still form when warm water evaporates into cooler air. In that sense, the oceans of distant worlds would feel strangely familiar, even though their skies might glow with different colors, even though their stars might appear dimmer or redder than our sun, even though their planets might be larger, deeper, or colder. The water itself would behave in the same quiet way, flowing, circulating, responding to gravity and temperature. And if those oceans exist, they may already be part of long planetary histories unfolding over billions of years, long before humans began wondering about them, and long before our telescopes became sensitive enough to notice their presence. Some of those worlds may have formed oceans early in their history, rain falling onto young planets, water gathering into seas, currents forming beneath unfamiliar skies. Other worlds may have gained water later, delivered by comets or icy bodies drifting inward from colder regions. And still others may have lost their oceans slowly as stars brightened or atmospheres changed. Across the galaxy, the story of water continues evolving on countless worlds, each planet writing its own quiet chapter. Yet all of those chapters share a common beginning. Water formed in ancient stars, hydrogen and oxygen meeting within the expanding clouds of stellar remnants, those atoms drifting through space until gravity gathered them into new systems, new stars, new planets, new oceans, and now, billions of years later, the light from those distant systems is just beginning to reach our telescopes, tiny signals traveling across unimaginable distances, carrying faint traces of the worlds where they began. Somewhere among those signals may be the subtle signs of distant oceans, seas that have never been seen directly, yet whose presence may already be written quietly into the light of their stars. And when we look up at the night sky, we are looking toward those distant places, toward stars that may be illuminating oceans circling far beyond our solar system, worlds where waves move slowly beneath unfamiliar constellations, where clouds drift across endless seas, where deep currents travel quietly through darkness beneath alien skies, all of it happening now, far away, patient, unhurried, part of the same vast universe that shaped the oceans here on Earth. And as we imagine those distant oceans, it becomes gently clear that the universe is not only a place of stars and planets, it is also a place of environments, whole planetary systems where weather unfolds, where heat moves through oceans and atmospheres, where chemistry slowly rearranges matter over long spans of time. When we first look at the night sky, the stars can seem like distant points of light, quiet, unchanging, but each of those lights may illuminate entire families of worlds, planets circling slowly in orbit, moons drifting around giant planets, comets passing silently through outer regions of those systems. And somewhere within many of those places, water may be present, sometimes frozen, sometimes drifting through the air as vapor, sometimes gathered into lakes or oceans. One of the most intriguing ideas scientists explore today is how common water-rich planets might actually be. Early studies suggested that Earth-like worlds with shallow oceans and continents might be relatively rare. But ocean planets, worlds covered by deep global seas, may be far more abundant. During planetary formation, water-rich materials can accumulate in large quantities. If enough water gathers on a forming planet, it may cover the entire surface before continents ever emerge. Instead of oceans filling basins between land masses, the water becomes the dominant feature of the planet itself. The entire world becomes a single connected ocean. In such places, there may be no shorelines at all, no beaches, no cliffs rising above the waves, only water stretching continuously across the surface of the planet, storm systems forming above warm regions, clouds drifting slowly across the sky, rain falling into seas that circle the entire globe. The depth of those oceans could also be extraordinary. On Earth, the deepest part of the ocean, the Mariana Trench, reaches about 11 kilometers below the surface. That depth is already immense. The pressure there is more than 1,000 times greater than at sea level. Yet on many theoretical ocean planets, the water layer could extend far deeper, dozens of kilometers, perhaps even hundreds. At those depths, the pressure becomes so extreme that water changes into unusual forms of ice. Even though the temperature remains relatively warm, the pressure forces the molecules into dense crystalline structures. These forms of ice do not float like the ice in Earth's oceans. Instead, they sink. They form layers deep beneath the liquid ocean, between the ocean above and the rocky interior below. This creates a strange planetary structure: liquid water at the top, a thick layer of high-pressure ice beneath, and the rocky mantle lying even deeper below that. In such worlds, the ocean may not touch the rock directly. Instead, the water rests above this deep ice layer. Scientists sometimes call these environments water worlds or Hycean planets. The term Hycean comes from combining the words hydrogen and ocean, reflecting the idea that some of these planets may possess thick, hydrogen-rich atmospheres above their global seas. These atmospheres could trap heat, allowing liquid water to remain stable even at distances from their stars where Earth-like planets might freeze. Because hydrogen is very effective at trapping warmth, even a relatively small amount could help maintain liquid oceans. This means that Hycean planets might exist across a wider range of distances from their stars than previously expected. Some may orbit in regions where Earth would be far too cold. Yet, beneath their atmospheres, oceans may remain liquid. These ideas remain part of active scientific research. Astronomers are still gathering evidence, still refining models, still searching for clearer signals in the faint light reaching our telescopes. But each new observation brings a little more clarity, And with that clarity comes an expanding sense of how diverse planetary environments can be. For centuries, Earth was the only known ocean world. Now we know of several within our own solar system that may contain hidden oceans. And beyond our solar system, thousands of planets have already been discovered. Some of them rocky, some gaseous, some likely rich in water. Each discovery adds another quiet reminder that the universe is larger and more varied than we once imagined. Worlds of lava, worlds of ice, worlds of clouds, worlds of endless ocean. When scientists describe these environments, they often do so carefully, not with certainty, but with possibility, because the universe continues to surprise us. Planets appear in places we once thought impossible. Atmospheres behave in ways we did not expect. Water appears where we thought none could survive. And sometimes the most familiar substances, rock, air, water, combine in ways that create entirely new kinds of worlds. Yet through all these variations, certain patterns remain. Gravity shapes planetary orbits. Stars provide energy. Chemistry governs how molecules interact. And water continues to flow through all of these systems, quietly adapting to whatever conditions it encounters. In that way, water becomes one of the most patient travelers in the cosmos, formed in ancient stars, carried through clouds of gas and dust, frozen into comets, delivered to young planets, gathered into oceans, evaporated into atmospheres, frozen again into ice, and then, perhaps, melted once more when conditions allow. The cycle repeats across astronomical timescales, across planets we may never visit, across oceans we may never see. Yet, the same molecule continues its quiet journey through the universe. 2 hydrogen atoms, 1 oxygen atom, a structure so simple that it seems almost ordinary. And yet, when billions upon billions of those molecules gather together, they create something immense. Seas, clouds, rain, currents moving through darkness beneath planetary surfaces, all of it unfolding slowly across the vast distances between the stars. And somewhere, at this very moment, those distant oceans may already be in motion. Waves rising beneath unfamiliar constellations, clouds drifting across alien skies, deep currents moving through water that has never known the warmth of Earth's sun. All of it happening quietly, patiently, as the universe continues its long and gentle work of shaping worlds. And when we pause and consider all of these possibilities together, the picture that begins to form is surprisingly calm. The universe is not only a place of violent explosions, collapsing stars, and enormous gravitational forces. It is also a place where slow processes unfold with extraordinary patience, planets forming grain by grain inside quiet disks of dust, atmospheres slowly gathering around young worlds, water condensing into clouds, rain falling into oceans that may persist for billions of years. In many ways, the formation of oceans is one of the gentlest planetary processes that exists. It happens slowly, gradually, molecules gathering together as temperatures cool, water vapor drifting through the air until it condenses, droplets forming inside clouds, those droplets growing heavier, eventually falling back toward the surface, rain after rain after rain, until basins fill, until seas begin to spread across the planet, until waves move across open water beneath a sky that may have never before reflected light from an ocean. On Earth, this process likely took place very early in our planet's history, after the surface cooled enough for liquid water to remain stable. vast amounts of water vapor in the atmosphere condensed for long stretches of time. Rain may have fallen continuously, storm systems circling the young planet, water collecting in low regions of the crust, gradually forming the first oceans. Those early oceans may have looked very different from the seas we know today. The atmosphere above them contained different gases. The continents had not yet formed as they exist now. Volcanic activity was more intense. Yet, even under those unfamiliar conditions, the basic behavior of water remained the same. It flowed, it pooled, it moved under gravity and temperature, and slowly, the first great oceans of Earth emerged. A similar story may have played out on many other worlds. Young planets cooling after their formation, atmospheres thick with water vapor, clouds forming above dark planetary surfaces, rain falling steadily for long periods of time, and eventually, oceans gathering where water could remain stable. On some planets, these oceans may have remained shallow. On others, they may have grown deep enough to cover the entire surface, each world finding its own balance between gravity, temperature, atmosphere, and chemistry. Of course, not every planet reaches that balance. Some worlds remain dry, others lose their water to space, but across the vast number of planets in our galaxy, even rare combinations of conditions may occur many times, which means that ocean worlds may not be unusual after all. They may simply be part of the natural diversity of planets. When astronomers look at distant stars, they are beginning to see this diversity more clearly. Some stars host tightly packed systems of small rocky planets. Others host giant planets orbiting far from the star. Some systems contain planets locked in delicate orbital resonances, moving in complex gravitational patterns. And among all of these different arrangements, there may be many places where water gathers into oceans, some shallow, some deep, some hidden, some stretching across entire planets. In each of those places, the same quiet physical laws apply. Gravity pulls water toward the lowest regions. Temperature determines whether it freezes or evaporates. Pressure influences how molecules arrange themselves. The chemistry remains the same. Even across distances of hundreds or thousands of light years, the water in those distant oceans behaves just as it does here. That continuity is one of the quiet beauties of science. The universe follows consistent rules. The physics of a wave breaking on a beach in Earth's ocean is governed by the same principles that would shape waves on an ocean planet circling a distant star. The molecules do not change. The forces do not change. Only the environment around them shifts. And so, the oceans of other worlds, if they exist, would still move in recognizable ways. Winds passing across the surface would generate waves. Currents would carry heat from warmer regions toward cooler ones. Clouds would form where evaporation rises into the atmosphere. Rain would fall back into the sea, a cycle repeating again and again across time. It is possible that on some distant ocean planets, this cycle has already continued for billions of years, long before humans learned to build telescopes, long before we wondered whether oceans existed beyond our solar system. Those distant seas may already have experienced countless storms, countless calm days beneath quiet skies, countless slow currents drifting through darkness far below the surface, all of it unfolding quietly, unnoticed across the vastness of space. And even now, as our telescopes continue searching the skies, we are only beginning to detect the faintest hints of those worlds, small shadows passing in front of distant stars, subtle patterns in the light that reaches our instruments, clues that somewhere far away, beneath unfamiliar skies, oceans may already exist, worlds where waves move slowly beneath alien constellations, where clouds gather above endless seas, where deep currents circulate through water that formed billions of years ago in ancient stars. All of it part of the same cosmic story that shaped the oceans of Earth. A story written in water, a story unfolding quietly across the galaxy. And tonight, as you listen and perhaps begin to drift toward sleep, it can be comforting to remember that those distant oceans, whether visible or hidden, are part of the same universe that surrounds us here, a universe where even the smallest molecules can gather together and shape entire worlds, where water flows patiently across planets, where clouds rise and fall beneath distant stars, and where, far beyond the reach of our eyes, oceans may already be moving softly in the dark. And somewhere along that long cosmic story, there is a quiet moment when the scale of it all becomes easier to feel, not to calculate or measure, just to sense, because when we talk about distant oceans, the distances involved are almost beyond ordinary imagination. Many of the planets astronomers study lie dozens, hundreds, or even thousands of light years away. A single light year is the distance light travels in 1 year, about 9.5 trillion kilometers. Light moves faster than anything else we know. Yet even light takes years to cross the gulf between stars. So when astronomers observe a planet 100 light years away, the light they see tonight actually left that star a century ago, long before most of the technology we rely on today even existed. And during all that time, the planet itself has continued moving along its orbit. Its oceans, if they exist, have continued shifting beneath its atmosphere. Storms may have formed and faded. Clouds may have crossed entire hemispheres. Rain may have fallen into seas that have never been seen directly, all while the light carrying the faintest hints of that world slowly traveled through interstellar space toward Earth. This is one of the quiet wonders of astronomy. When we look outward, we are also looking backward through time. The signals reaching our telescopes are ancient messages, not written deliberately, of course, but carried naturally by the movement of light across space. Each photon that arrives has traveled an immense journey, passing through empty regions between stars, crossing enormous distances where nothing interrupts its path, until at last it reaches a mirror on a telescope somewhere on Earth. And within that tiny signal, scientists search for patterns, small variations in brightness, subtle fingerprints of molecules in a planet's atmosphere, clues that might reveal the presence of water vapor, clouds, or perhaps entire oceans below. It is a delicate process, one that requires patience and careful observation. But little by little, these methods are improving. The telescopes of the coming decades may be able to gather far more detailed information. Some may even allow astronomers to observe the reflected light of distant planets directly, instead of only detecting the faint shadows they cast while crossing their stars. We may begin to see the planets themselves, tiny points of light beside much brighter suns. From that light, scientists may eventually detect signs of oceans, water reflecting starlight from a planetary surface, cloud patterns drifting across the atmosphere, even the glint of sunlight reflecting off waves, a faint sparkle from a distant sea. These possibilities remain part of the future of astronomy. Yet even now, The idea that oceans may exist beyond Earth has already reshaped our understanding of the cosmos, because for most of human history, the oceans seemed like something deeply tied to our own planet. They were part of Earth's identity. The blue surface seen from space, the waves and tides that have shaped coastlines for billions of years. But as our knowledge expands, we begin to see that oceans may not be unique. They may be one expression of a larger cosmic pattern, a natural outcome when water, gravity, and planetary conditions come together in the right balance. And if that is true, then somewhere out there, distant ocean worlds may be experiencing moments very much like the ones we know here. A calm surface under a quiet sky, winds brushing across open water, clouds slowly gathering above warm seas, deep currents moving through darkness far below, none of it aware that its faint light may one day reach a telescope on another world, none of it aware that distant observers are wondering what lies beneath those clouds, all simply unfolding according to the quiet rules of physics and chemistry. The universe, in that sense, is not only a place of extremes, it is also a place of familiarity. The same laws that shape waves along Earth's coasts shape the behavior of water everywhere. The same chemistry that allows clouds to form above our oceans allows clouds to form on distant planets. The same molecular dance that takes place inside a drop of water here occurs in every ocean throughout the cosmos. 2 hydrogen atoms, 1 oxygen atom, arranged in a structure that encourages molecules to cling gently to one another, forming droplets, forming streams, forming seas. A simple arrangement that leads to something vast when multiplied across a planetary scale. Oceans that move with tides and storms, oceans that store heat and shape climates, oceans that quietly reshape the worlds they cover. And somewhere in the galaxy tonight, beneath a sky illuminated by a distant star, an ocean may already be rising and falling with slow planetary rhythms, waves forming under winds that no human has ever felt, clouds drifting above seas that have never been seen, deep currents moving patiently through darkness beneath alien skies, all of it continuing its quiet motion while the light from that distant world begins its long journey across the stars. And as that light continues traveling through the quiet darkness between the stars, the oceans it left behind continue their own slow rhythm. Nothing there pauses. Nothing waits for an observer. The waves rise and fall whether anyone sees them or not. Clouds gather and dissolve whether anyone studies their patterns. Rain falls into distant seas without leaving a sound that could ever reach us. That is one of the quiet truths about the universe. Most of what happens in it unfolds unseen. Stars form inside clouds of dust long before any telescope notices them. Planets cool and gather oceans long before any civilization wonders about their existence. And on many of those worlds, the processes that shape oceans may have already been underway for billions of years, long before humans ever walked beside the sea on Earth, long before the first ships crossed our oceans, long before anyone asked whether water might exist elsewhere in the cosmos. Those distant worlds may already have experienced countless cycles of weather, storms forming above warm regions of ocean, winds sweeping across planetary surfaces, clouds drifting slowly through alien atmospheres, rain falling into seas that stretch uninterrupted across the horizon, and deep beneath those surfaces, the ocean itself may be moving quietly through layers of darkness, currents circulating slowly through immense depths, heat rising from the rocky interior of the planet, minerals dissolving into the surrounding water, all part of a vast system that evolves gently over time. When we think of oceans here on Earth, we often imagine the surface first, waves rolling toward the shore, the rhythm of tides, the changing colors of water under different skies. But most of the ocean lies far below the reach of sunlight, a world of calm pressure and slow movement. On Earth, more than 90% of the ocean exists in darkness, and that same quiet darkness may exist in the oceans of other worlds. Layers of water stretching downward beneath the reach of light, temperature shifting only slightly over great distances, pressure increasing steadily as the ocean deepens. In those depths, the movement of water may be so slow that a single current could take centuries to complete its path. A quiet circulation connecting different regions of the planet, carrying heat, carrying dissolved minerals, linking distant parts of the ocean together. If such oceans exist on distant exoplanets, their deep layers may remain among the most stable environments in the universe, shielded from storms, shielded from sudden changes in temperature, protected beneath thick atmospheres or layers of ice. In those calm depths, chemistry may unfold with extraordinary patience, molecules drifting slowly through the water, occasionally meeting, occasionally forming new structures, energy flowing gently through chemical gradients. On Earth, similar processes may have played a role in the earliest stages of life, deep ocean environments where chemistry had time to experiment with different combinations, where energy from hydrothermal vents fueled complex reactions, where molecules slowly assembled into structures capable of copying themselves. Whether anything like that has happened elsewhere remains one of the great unanswered questions. But the presence of water alone creates a setting where such possibilities can exist. A liquid medium where molecules move freely, where heat can circulate, where chemistry can become elaborate over long spans of time. And yet, even without life, oceans themselves remain beautiful systems. They shape the climate of planets. They regulate temperature. They create clouds and weather. They influence the evolution of atmospheres. Across the galaxy, wherever oceans gather, they become part of the story of that world, a story unfolding quietly through cycles of evaporation, condensation, and circulation. Water rising into the sky, water falling again as rain, water freezing into ice and melting again when conditions change. The same gentle transformations repeating across countless environments. When astronomers search for ocean planets, they are searching for those stories, not simply bodies of water, but planetary systems where water participates in a long and complex dance with gravity, heat, atmosphere, and chemistry, each world with its own balance, its own climate, its own quiet rhythm of oceans and skies. And even though those worlds lie far beyond our reach, the light they send across space continues to arrive here. A faint glow carrying traces of their existence, signals that tell us planets are there, that atmospheres surround them, that water may be present. Each observation expanding our understanding of what kinds of worlds exist in the universe. Each discovery reminding us that the cosmos is far richer than we once imagined, not only filled with stars and galaxies, but filled with environments, planets with weather, moons with hidden seas, worlds where oceans may stretch from horizon to horizon, all moving quietly beneath distant skies. And as those distant oceans continue their slow motion beneath alien constellations, their light begins its patient journey toward us, traveling year after year across the vast quiet between stars, until one small portion of that light finally reaches a telescope on Earth. And in that moment, across unimaginable distance and time, we learn a little more about the hidden waters of the universe. The night sky above us can sometimes feel very still, a quiet dome of distant stars, pinpoints of light scattered across darkness. But behind that stillness, the universe is full of slow movement, stars drifting through the galaxy, planets circling their suns, clouds of gas collapsing to form new systems. And on some of those distant worlds, oceans may be moving as well, waves rising and falling beneath unfamiliar skies, clouds forming above seas that stretch far beyond any horizon, rain returning again and again to water that may have been flowing for billions of years. It can be comforting to remember that these distant oceans, if they exist, are shaped by the same simple physics that shapes the waters here on Earth. The pull of gravity guiding each wave, the quiet energy of sunlight warming the surface, the deep currents slowly redistributing heat through immense volumes of water, even across the vast distances of space. Those patterns remain familiar. The molecules behave the same way. Water still flows, clouds still gather, rain still falls, and over long stretches of time, oceans continue their patient cycles, evaporating, condensing, freezing, melting, moving again. Earlier tonight, we wandered through many of the ways oceans might appear across the universe. We imagined planets completely covered by deep global seas, worlds where water stretches uninterrupted from horizon to horizon. We thought about hidden oceans sealed beneath thick layers of ice, quiet seas moving slowly beneath frozen surfaces. We explored the strange possibilities of water under immense pressure, where deep layers of exotic ice may form far below the surface. And we considered how astronomers search for these worlds through the faint signals carried by distant starlight, tiny shadows crossing a star, subtle fingerprints of molecules in a planet's atmosphere, clues that hint at the presence of water far beyond our solar system. All of these discoveries are still unfolding. Astronomy is a young science compared to the immense age of the universe. Only recently have we begun detecting planets around other stars. Only recently have our instruments become sensitive enough to study the atmospheres of those worlds. And with each improvement in our technology, the picture grows a little clearer. More planets discovered, more atmospheres analyzed, more possibilities revealed. Perhaps in the coming decades, scientists will detect clearer signs of ocean worlds. Perhaps telescopes will observe the faint glimmer of light reflecting from distant seas, or the shifting brightness of clouds drifting across alien skies. Each new observation will add another piece to the quiet puzzle of how water shapes the universe. But even now, without seeing those oceans directly, we can sense the larger pattern. Water is everywhere, in clouds between the stars, in icy comets drifting through planetary systems, in frozen moons and hidden subsurface seas, and very likely in oceans on planets far beyond our own. The same small molecule repeating its quiet work across the cosmos. 2 hydrogen atoms, 1 oxygen atom, a structure so simple it seems almost ordinary, yet capable of shaping entire worlds, capable of forming seas that store heat, move currents, and sustain chemistry across billions of years. And tonight, as you rest here on Earth beside our own ancient oceans, it is gentle to imagine that somewhere far away, beneath the glow of another star. A distant sea may already be moving, waves rising slowly across the surface of an unseen planet, clouds gathering above endless water, deep currents circling quietly through darkness far below, all of it unfolding without hurry, part of the same universe that surrounds us here, part of the same long story written in water across the galaxy. And if your thoughts begin to drift now, that is perfectly all right. You do not need to hold on to any of these details. The oceans of distant worlds will continue moving whether we remember them or not. Their waves will rise and fall beneath alien skies. Their clouds will form and dissolve in quiet cycles. And somewhere out there, beneath stars we may never visit, water will keep flowing gently through the vast calm of the universe. You can simply let that thought settle softly and allow yourself to rest